Why were gamma-ray bursts first mistaken for nuclear blasts? How can a flash lasting seconds outshine billions of years of sunlight? What cosmic events create these powerful bursts? In the stillness of a starry night, the universe seems to hold its breath. Stars shimmer softly against a velvet darkness, distant and silent. To our eyes, nothing appears to change, each pinpoint of light steady and eternal. It is a scene of calm that has persisted for ages. And yet, in this deep quiet, something unexpected can happen in the blink of an eye. Imagine gazing up at this tranquil night sky. All is quiet, the darkness vast and comforting. Then, for a split second, a new light flares and vanishes. It appears suddenly, a tiny pinprick in the dark, and before you can even be sure it was real, it's gone. The night is silent once more, as if nothing happened at all. But in that brief moment, the universe revealed a secret, a flash so swift and so powerful that it challenges our understanding of what can happen in a heartbeat of time. These fleeting cosmic sparks are known as gamma-ray bursts. They erupt without warning in far-off reaches of space, releasing more energy in a moment than many stars do in a lifetime. Yet, from here on Earth, they do not announce themselves with bright colours we can see or with thunder we can hear. To an ordinary sky watcher, the flash would pass unnoticed. Only specialised instruments, watching vigilantly, catch the sudden surge of invisible light from across the cosmos. Invisible light. It's a strange idea. What does it mean to see a flash that our eyes cannot see? The light of a gamma-ray burst lies beyond the colours of the rainbow, beyond even the purples and blues. It resides in the realm of gamma rays, the most energetic form of light. Our human eyes evolved to see only a narrow band of colours, the gentle spectrum from red to violet that sunrises and rainbows paint across the sky. But gamma rays are a colour beyond sight. They carry so much energy that our eyes and even Earth's atmosphere block them out, keeping us blissfully unaware of the universe's fiercest fireworks. So when a gamma-ray burst ignites in the distant dark, it doesn't shine red or blue or white to our gaze. It is more like a sudden gust of wind in a still night, felt but not seen, known only by its effect on the world around it. Detectors in space can feel this burst of energy. They translate it into signals and data that scientists on the ground can understand. Through these technological eyes, we learned that these hidden explosions were happening, brief and brilliant, scattered all across the sky. The discovery of gamma-ray bursts was a complete surprise. In the late 1960s, during a time when humanity's eyes were turned toward threats much closer to home, a handful of satellites quietly patrolled Earth's orbit. They were launched during the Cold War, tasked with a very specific job: listen for the telltale gamma-ray flashes of nuclear weapons tests. High above the atmosphere, these sentinels floated in silence, waiting and watching for any sign of human folly. For a long while, they heard nothing unusual. Then, on a day like any other, the satellites detected a flash. It was sudden, intense, but it did not fit the pattern of a bomb. It seemed to come not from Earth's surface at all, but from somewhere out in space. The instruments recorded a burst of gamma rays unlike anything known. One can imagine the confusion and intrigue as the data arrived. There, amid the routine vigil for weapons, was evidence of a different kind of detonation, one that came from the heavens themselves. At first, this finding was cloaked in secrecy. The discovery sat quietly in classified reports, an odd curiosity. Only years later were the observations declassified and shared with the wider scientific community. When astronomers around the world learned of these mysterious gamma flashes, they were astonished. What could possibly be producing such powerful bursts of energy, appearing and disappearing in seconds? A mystery was unfolding, and the chase to understand it had begun. For years, gamma-ray bursts remained one of the sky's best-kept secrets. They were elusive, here and gone so quickly that gathering clues was incredibly difficult. Telescopes and detectors would catch a burst, but by the time anyone tried to point another instrument at its location, it had vanished completely. It was like trying to catch lightning in a bottle when you don't know when or where the next storm will strike. Scientists collected what data they could, marking each burst on a map of the sky. As those maps filled in, a surprising pattern emerged, or rather, a surprising lack of pattern. The bursts were everywhere. No corner of the sky was favoured. They did not cluster around the band of the Milky Way, or towards any familiar constellation. They seemed to be scattered randomly, appearing in every direction with equal probability. To astronomers, this was a profound clue. If these bursts were coming from within our own galaxy, one might expect to see more of them toward the dense heart of the Milky Way, or along its glowing disk. But instead, the distribution was uniform, as though the bursts were sprinkled throughout the cosmos, far beyond our galactic neighborhood. This realization was both exciting and daunting. Exciting because it hinted that gamma-ray bursts were not minor local flares, but massive events in the distant universe. Daunting because if they were so far away, how incredibly powerful must they be to still be detectable from Earth? Each burst, even billions of light-years distant, was bright enough in gamma rays to be noticed over the vast gulf of space. It was as if the universe had been lighting invisible firecrackers at unimaginable distances, and only now had we developed the senses to perceive them. Still, knowing they came from far away did not immediately reveal what they were. The bursts themselves were over almost as soon as they began, leaving precious little information. It was like witnessing only the flash of a firework, but not seeing the firework itself, or hearing the boom that follows. Astronomers yearned for more data, more clues, something to connect these bursts to real objects out there in the cosmos. In time, a clever strategy began to pay off. Rather than catching just the flash, telescopes started to chase the afterglow. When a gamma-ray burst goes off, it isn't always completely gone in an instant. Sometimes, after the initial burst of gamma rays, a softer glow lingers. This glow can shine in X-rays, visible light, even radio waves, forms of light that we can capture with different telescopes. These afterglows are like the fading embers of a cosmic fire, gently illuminating the scene of the explosion after the brightest flames have died down. Imagine a sudden flare in the sky that leaves behind a faint, warm glimmer, slowly dimming. If telescopes can quickly turn to where the burst occurred, they might catch those fading embers before they disappear. And that is exactly what began to happen in the late 1990s. For the first time, astronomers managed to track down a gamma-ray burst's afterglow, pinpointing the location where the burst had occurred. When they focused on that spot with powerful telescopes, they discovered something remarkable. They could see a distant galaxy at the very place the burst had originated. Here was the proof. Gamma-ray bursts were not nearby at all. They were taking place in galaxies millions upon millions of light-years away. In fact, many were billions of light-years distant, so far that the light from those bursts had left its source long before Earth even existed as a planet. We were catching echoes of immensely ancient and remote catastrophes. Learning the distances to these bursts was like finally hearing the faint rumble of thunder after seeing a flash of distant lightning. It confirmed how far away the storm was, and how powerful it must have been for its light to reach us. The term distance like thunder speaks to that realization. Just as thunder rolling in the distance tells us a storm is far but strong, measuring the vast gap between us and these bursts told us we were witnessing some of the most titanic explosions the universe has ever produced. With distances known, the next questions came into sharper focus. What could cause such energy to be unleashed in such a brief moment? The clues slowly gathered from different afterglows started to paint a picture. Not all gamma-ray bursts were identical. Some lasted longer, tens or even hundreds of seconds, and often these showed a particular pattern of afterglow, and occasionally a telltale sign of a star's death. Others were much shorter, mere fractions of a second to a couple of seconds, and they seemed to lack any obvious sign of a star exploding. It was as if nature was producing two distinct kinds of cosmic firework, one longer lasting, perhaps coming from the catastrophic demise of a single massive star, and another blink quick, possibly from a more sudden collision of two incredibly dense objects. Astronomers began referring to these as the two families of gamma-ray bursts, long bursts and short bursts. The long ones, those that lingered for dozens of seconds, hinted at origins in young star-forming galaxies, where massive stars live out their brief lives and die in spectacular fashion. The short bursts, so brief you might miss them if you blink, pointed to old regions of the universe, places where ancient remnants like neutron stars might drift in pairs until they spiraled into each other. The split between long and short mattered, because it suggested there isn't a one-size-fits-all explanation for all gamma-ray bursts. The universe, it seemed, had at least two ways of forging these brilliant flashes, two different kinds of cosmic engines setting them off. Even the short and long labels can be misleading in their own way, because everything about gamma-ray bursts is fast, almost beyond comprehension. Consider this. A long burst might last for 50 seconds. 50 seconds doesn't even fill a single minute of time. We have songs and spoken sentences longer than that. And yet, within those scant seconds, a burst can pour out more energy than our sun will emit in its entire 10 billion year lifetime. Now imagine a burst that lasts just 1 second, or even a tenth of a second. It's like a camera flash at a cosmic scale, so quick that if you looked away and then back again, you'd never know it happened. In that split second, energies are unleashed that defy easy imagination, energy that dwarfs anything our human technology can create. How fast is fast? In the realm of gamma-ray bursts, it is the speed of a cosmic heartbeat releasing the power of millions of suns. Such speed and power stretch our imaginations. We are used to gentle, predictable rhythms, the sun rising each day, the steady orbits of planets, the slow aging of stars across eons. Gamma-ray bursts are the opposite, sudden, unpredictable, and fleeting. They remind us that the universe can surprise us, that even in what seems like a tranquil sky, there can be moments of unimaginable violence. And yet, there is a strange reassurance in their transience too. The burst comes, it shines with overwhelming brilliance, and then it is gone, leaving the darkness as quiet as before. The cosmos returns to calm, as if even such an outburst is just a brief note in a grand cosmic lullaby. As the pieces of the gamma-ray burst puzzle came together, scientists realized they were, in fact, opening a door into one of nature's most profound events. Take the long bursts, for example. the ones that last the length of a leisurely breath. Evidence began to tie these longer flashes to the final moments in the life of a giant star. Picture a star dozens of times more massive than our Sun, burning brilliantly for millions of years. Eventually, the star's fuel runs low, and gravity begins to win the eternal tug-of-war at its core. In an instant, the core collapses in on itself, forming an extraordinarily dense object, often a black hole. When that happens, the star doesn't simply fade away. Instead, it can trigger a dramatic expulsion of energy. Jets of material, driven by the newborn black hole, or perhaps a fiercely magnetized neutron star at the core, blast outward through the collapsing star. These jets punch through the star's outer layers and erupt into space, carrying a tremendous amount of energy with them. If one of those jets is pointed in our direction, we see a gamma ray burst. It is as though, for a brief moment, a door into the star has opened, and through that door, we glimpse the raging furnace of creation and destruction inside. The burst itself is like the universe catching sight of that hidden interior, lit up by forces we are only beginning to understand. In the afterglow, we see the debris of the star's final moments, a kind of cosmic ash from the fire. Sometimes we even see a supernova's bloom in the days or weeks after a long burst, the dying star's more gradual farewell in visible light, confirming the connection. Standing at this threshold of understanding, we feel both enlightened and humbled. We know now that one kind of gamma ray burst signals the birth of a black hole from the death of a giant star, a moment of rebirth hidden in violence. We suspect that the other kind, the very short bursts, herald a different kind of event, perhaps the merger of two ancient stars that had long ago lived quiet lives, only to collide and create one final blaze of glory. Each burst, long or short, is an announcement of something extraordinary, a massive change, an ending that is also a beginning, a transformation etched across the cosmos in light we cannot see with our eyes, but can finally detect with our instruments. And so, the story of gamma ray bursts has unfolded from a quiet secret into a grand cosmic tale. We started with a silent night and a sudden spark in the dark, barely there and nearly missed. We followed the clues, an invisible flash, a covert discovery, a map without pattern, a chase after fading embers, and the realization of immense distances and energies. We learned that there are different kinds of sparks, some longer, some shorter, each with its own origin story. Now, we find ourselves peering through the open door into the heart of a dying star, knowing that we stand on the edge of even deeper revelations. The night sky above is still tranquil and comforting to the eye. Most of the time, it changes only slowly as the earth turns and the seasons pass. But now we know that hidden in that calm vista are moments of incredible drama playing out in distant galaxies. We know that somewhere, far away, a star has just ended its life in a magnificent burst that outshines entire galaxies for an instant, or perhaps, in some quiet corner of the universe, two long-dead stellar remnants have finally met, spiraling into each other in darkness and unleashing a surge of gamma rays. These events send their echoes across space and time, and decades or eons later, our instruments may catch that echo. As we let our gaze rest on the stars tonight, we can carry this awareness gently. The universe has its secrets, and even in its great silence, it speaks in bursts of energy and light beyond human sight. Each gamma-ray burst is a message from the cosmos, a reminder of how much we have yet to learn and how beautifully mysterious our universe remains. Our journey through this understanding is not over. In fact, it feels as though we have just opened a book to its middle chapters, glimpsing a narrative of creation and destruction on the grandest scales. There is so much more out there, quietly waiting for curious minds and sensitive instruments to uncover. For now, we stay a while longer in the calm of the night, thoughtful and a bit awed. The cosmic show continues above us, quiet and hidden, yet astonishing when revealed. And as we breathe slowly under the starlight, we know that the tale of the universe's ultimate explosions is still unfolding, waiting for us to follow its trail into deeper realms of wonder. Far out, in a quiet corner of a galaxy, a colossal star shines with fierce brilliance. It is many times the mass of our sun, pouring out light and heat at an astonishing rate. In this patch of the cosmos, the star dominates its surroundings, its radiance drowning out that of lesser suns. Yet for all its power and majesty, the life of this giant will be surprisingly brief. For millions of years before this moment, cosmic forces conspired to create such a star. In a faraway nebula, a dense cloud of gas and dust began to collapse under its own gravity. That collapsing cloud gave birth to a clutch of new stars, and among them emerged this giant, weighing perhaps 50 times more than the Sun. From the start, it outshone and outmassed its siblings, gathering more and more material until it became a dominant cosmic furnace. In its very infancy, it was clear this star would burn with uncommon fervour, and use up its life fuel in a fraction of the time of an ordinary star. In the star's core, nuclear reactions rage at a tremendous pace. The great weight of the star presses inward with intense gravity, raising the central temperature and pressure to extraordinary levels. Under these conditions, hydrogen fuses into helium rapidly, releasing prodigious energy. This massive star is effectively burning its candle at both ends, consuming its fuel far more quickly than a smaller star ever could. For a star like our Sun, life is leisurely, measured in billions of years. But this giant star will exhaust its core hydrogen in just a few million years, a blink of an eye by comparison. The more massive the star, the faster it must burn to support its own weight, and this one blazes intensely. It shines millions of times brighter than the Sun, living on overdrive and racing through its life stages with breathtaking speed. This star is like a cosmic firework, destined to dazzle and fade quickly. Smaller stars might be like steady candles glowing for billions of years, but this massive star is more akin to a roaring bonfire that consumes everything rapidly. It epitomizes the idea that the brightest flame burns the shortest time. In every passing million years, mere moments on the cosmic clock, it expends an enormous store of energy. The star lives on overdrive, as if aware that its clock is ticking fast. The star's brilliance does more than shine. It reshapes its surroundings. Intense light and searing heat pour off its surface, driving a powerful stellar wind outward. Gases and particles stream into space, carving out a bubble in the interstellar clouds around the star. The nearby nebula glows under the onslaught, its delicate filaments pushed aside by the giant's outflow. Even during its short life, the massive star leaves an enduring imprint on its neighborhood, sculpting cosmic scenery with its ferocious energy. As time flows, the giant star rushes through successive fuel sources in its core. After quickly depleting its hydrogen, it begins to fuse helium into carbon and oxygen. Not long after, those new elements themselves ignite in turn, carbon burning to neon and magnesium, then heavier still. Each stage of fusion runs faster than the last, as if the star is sprinting toward a finish line. Deep inside, layers of different elements form like the rings of a tree, testimony to each fleeting phase of the star's burning life. From the outside, the star also undergoes dramatic changes as it ages. It may swell and cool into a red supergiant, its outer layers expanding outward and shining with a ruddy hue. Alternatively, it might shrug off those outer layers entirely, uncovered by the power of its own radiation. In that case, the star becomes a blazing blue-white core exposed to space, a kind of star known to astronomers as a wolf-rayet. Whether bloated and red or stripped and blue-hot, the giant is now in its final stages, unstable and nearing the end of its life. By now, deep within, the star's core is laden with the heaviest products of all those reactions. The nuclear fires have created elements like magnesium, silicon, and sulfur, which in turn gave way to even heavier elements. At the very center, a core of iron is beginning to form, a dense, inert heart that grows with every passing moment. Iron is different from the fuels that came before. Fusing iron doesn't release energy, it consumes it. As this iron heart enlarges, the star is unknowingly approaching a critical threshold. Its extravagant life, which burned so brightly, is about to reach a sudden and violent climax. At last, the moment arrives when the core can no longer bear the crushing weight of the star above. The iron heart at the center has grown too massive and can provide no further energy. In a fraction of a second, the core buckles. Gravity pulls it inward in a catastrophic collapse. This dramatic turning point comes without fireworks or sound. Deep inside the star, it happens in eerie silence. As the core implodes, the fundamental structure of matter begins to break down. Atoms are squeezed so tightly that electrons merge with protons, creating neutrons and releasing a flood of ghostly neutrinos. In an instant, the core shrinks from a sphere the size of a city to an object only a few kilometers across. The densities reached are unfathomable, far greater than anything on Earth. Within less than a heartbeat, a new ultra-dense core is born in the center of the star. For a brief and critical moment, the collapse is suddenly halted at that core. If the core slams to a stop on the pressure of closely packed neutrons, it becomes a newborn neutron star, extremely small and incredibly dense. In other cases, especially in a star this massive, even the neutrons cannot hold up, and the core continues collapsing into a nascent black hole. Either way, the infalling material from above crashes into an unyielding center. A powerful shockwave forms as matter rebounds, and huge amounts of energy are released, much of it in the form of neutrinos streaming outward. In those first split seconds of collapse, neutrinos pour out of the core in staggering numbers. These nearly massless particles hardly ever interact with matter, yet the flood is so immense that it helps blow the star apart from within. Trillions upon trillions of neutrinos race through the star's layers and into space, carrying away energy and information about the cataclysm. Alongside the shockwave, this burst of neutrinos is a silent herald of the disaster, escaping even before any light can. The star's outer layers, which had been supported for millions of years by the core's pressure, now come crashing inward. With nothing left to hold them up, these vast layers of gas free fall toward the center. Billions upon billions of tons of stellar material accelerate downward, heating up as they go. In this raging implosion, the once stable star is being torn apart from the inside. What was a giant sphere of hot gas is rapidly becoming a collapsing shell, hurtling inward under gravity's command. For now, all of this violence remains hidden beneath the star's surface. To any distant observer, the star has not yet betrayed its impending doom. The brilliant light from the surface continues almost as usual for the moment, giving no hint of the catastrophe unfolding within. But deep inside, a dramatic reversal is brewing. In the next instant, the implosion will give rise to an explosion racing outward, and the quiet will be broken by one of the universe's most powerful blasts. In the chaos, the fabric of spacetime itself may tremble. The asymmetric collapse and rebounding core send faint gravitational waves rippling outward. These subtle vibrations carry away a final whisper of the star's death throes. They will wash through the cosmos unnoticed by all but the most sensitive instruments. A fleeting murmur from the collapsing core. In the shattered heart of the star, a new and exotic object now resides. The core collapse has created either a black hole, an abyss of gravity, or a neutron star of extraordinary properties known as a magnetar. Either outcome is a cradle of darkness in the midst of chaos. These central engines are tiny in size, perhaps only tens of kilometers across, yet their gravity and energy dominate everything around them. This infant black hole or magnetar holds the key to what comes next in the unfolding cosmic drama. If a black hole has formed, it is a region of almost unimaginable gravity. It is an abyss from which not even light can escape. Around it, the remaining inner layers of the star swirl in a dense, frantic accretion disk. Gas and stellar debris spiral into the black hole at nearly the speed of light, heating up to searing temperatures. Magnetic fields twist through the disk, intensified by the rapid motion of charged particles. In this maelstrom, a tremendous amount of energy is being extracted from the infalling matter and from the black hole's spin, preparing to blast outward. If instead the core became a magnetar, it is no less extraordinary. A magnetar is a neutron star on overdrive, incredibly compact, perhaps spinning hundreds of times each second and crackling with magnetic fields trillions of times stronger than Earth's. This magnetic force is so extreme that it can distort atoms and make the space around it seethe with energy. The newborn magnetar is like a dynamo, converting its furious rotation into intense radiation and particle winds. Its magnetic field twists the surrounding gas violently, and pulses of energy surge out from its poles. In its own way, the magnetar too is primed to drive a colossal eruption from the dying star. In this brief, furious epoch, the collapsed core, whether black hole or magnetar, reigns over the chaos. This tiny engine, no larger than a city, is channeling energy on a mind-boggling scale. For a short time, it outshines the entire star and even whole galaxies, but all of its fury is trapped inside the stellar wreckage around it. The darkness of the black hole, or the fierce magnetism of the neutron star, is gathering what remains of the star's energy. It will soon launch that energy in narrow, focused beams that cut through the wreckage. For only tens of seconds, or a few minutes at most, this central engine will continue to drive the jets with tremendous power before finally exhausting its fuel. Within the collapsed star, forces are shaping the course of the coming explosion. The intense rotation and magnetic fields act like cosmic engines, channeling the fury into two oppositely directed funnels. Instead of an even blast in all directions, the energy finds preferred escape routes along the north and south poles of the core. Here, in these narrow funnels, the darkness at the center begins to spit out streams of light. A pair of jets is born, shooting outward from the heart of the dead star. Out from the chaos of the core, twin jets of energy erupt along the star's axis. They are narrow and extraordinarily bright, a pair of focused beams shooting in opposite directions. These jets carry away a stupendous amount of energy, but unlike an ordinary supernova explosion, they confine it to tight corridors. Each jet is like a cosmic drill or blowtorch, thrusting through the collapsing star from within, forcing a path to the outside. The dying star has effectively channeled its wrath into these two intense streams. Racing outward at near light speed, the jets pierce into the star's interior. Their leading edges plow ahead ferociously, compressing and heating any material in their way. In effect, each jet opens up a tunnel through the star's layers, a searing passage blown clear by sheer energy. Stellar material is swept aside or obliterated by the onrushing torrents of radiation and high-speed particles. These narrow rivers of light are literally boring through what remains of the star. Within each jet, conditions defy ordinary imagination. They consist of seething plasma, atomic particles accelerated to nearly the speed of light, and blinding gamma rays born from the heart of the explosion. The jets are threaded by intense magnetic fields that keep them tightly collimated, preventing them from fanning out too quickly. They are so fast and energetic that even time and space are subtly distorted in their frame. In these rushing torrents, matter and energy blur into one, all of it hurtling outward in a focused rage. For all their focus, the jets are not smooth streams, but wild, turbulent flows. Faster portions of the jet catch up with slower ejections, producing internal shock waves that ripple through the beam. These collisions within the jet create sudden surges of heat and light, adding to the burst's flickering brilliance. The magnetic fields lightly coil and snap in the turmoil, injecting bursts of energy that make the jet's brightness vary in intense, rapid flashes. Even as they tunnel outward in a straight line, within the jets, a chaotic dance of particles and fields is taking place. For a brief time, these jets remain trapped inside the dying star. All the while they continue to gorge on energy from the central engine, growing hotter and more forceful. The layers of the star above them are being shredded and pushed aside as the jets tunnel upward. The journey from the core to the surface might take only seconds, but in those moments, the jets gather strength. They are like pent-up geysers, ready to burst forth as soon as they reach the open sky of space. Each jet is remarkably narrow, perhaps only a few degrees across. If one could watch from afar, they would appear as thin, intense beams slicing out from the star's poles. Such focus means that only a small portion of the universe will be in their direct line of fire. All the energy of the explosion is channeled into these slender paths. For any worlds not lying along those paths, the death of this star might pass unnoticed. But for those in the way, an extraordinary beacon is about to appear. And then, the moment of liberation arrives. The first jet punches through the star's surface, bursting into open space. In that instant, pent-up brilliance floods outward, no longer confined by the dying star. The star's outer shell gives way immediately, vaporized and swept aside by the jet's onslaught. A tremendous flash of high-energy light explodes forth, announcing the gamma-ray burst to the universe. What was hidden deep inside just moments ago now blossoms into a beacon visible across cosmic distances. The gamma-ray burst has begun in earnest, a sudden outpouring of the most energetic form of light. In mere seconds, it releases more energy than a star like our Sun would produce in 10 billion years. The burst is ferociously bright, but it emanates mainly in gamma rays, invisible to human eyes, yet deadly and penetrating. If one could watch with the right instruments, they would see a rapid flickering and pulsing as the newborn jets expel their energy in waves. Each pulse of gamma rays is like a lightning flash from the core of the explosion, incredibly intense and brief. For the brief duration that it lasts, the gamma-ray burst outshines virtually everything else in the universe. At its peak, for those seconds or minutes, it can be the most luminous object in the sky. The jets, now free of the star, continue to spew energy, and the burst's brightness may rise and fall multiple times as the central engine feeds it. Eventually, as the engine exhausts its fury or the star's fuel is fully spent, the torrent of gamma rays begins to wane. The initial flash passes, making way for the next chapter of the event. Around the now exposed poles of the star, matter is blasted outward alongside the radiation. The once cohesive star is being thoroughly ripped apart. While the focused jets race ahead, the rest of the star's material also explodes more slowly in all directions. The surface layers, blown off by the shock and the emerging jets, expand outward as a hot, glowing shell. The star has met its violent end, and the gamma-ray burst is its opening cry. For observers in the cosmos, fortunate enough to be aligned with one of the jets, the burst is a momentary blaze of glory. Gamma rays surge past, followed by pulses of X-rays and a cascade of other radiation. For those few heartbeats, the universe is illuminated by this single, distant event. But as swiftly as it came, the brilliant flash begins to fade. The immediate drama of the burst is over, giving way to a slower, fading radiance known as the afterglow. The great flash of gamma rays may be over, but it is not the end of the event. In the wake of the burst, the sky around the shattered star begins to glow with a more subtle light. The jets that tore out of the star are now ploughing into the thin gas of interstellar space. In doing so, they create powerful shock waves that heat the gas and accelerate particles to incredible speeds. These shock fronts become moving beacons, generating an afterglow that can persist long after the initial gamma-ray fireworks have faded. As the jets slam into the surrounding medium, they send a shell of energized matter expanding outward at nearly light speed. The high-speed collision between the jet material and interstellar gas produces X-rays, ultraviolet light, visible glimmers, and radio waves. Bit by bit, this afterglow spreads across the electromagnetic spectrum. In the first moments and hours, the afterglow shines brightly in X-rays and visible light, a hot, bluish echo of the burst's energy. Over time, as the shock wave loses energy, the glow softens and shifts to longer wavelengths like red light and radio waves. At first, the afterglow can be almost as dazzling as a distant star at night, visible in high-energy radiation and even through optical telescopes. A day after the burst, it might still light up the cosmic canvas, though already dimmer than at the beginning. With each passing hour and each new day, the afterglow continues to fade, the radiation gradually weakening as the expanding shock cools and disperses. What started as a furious blaze becomes a gentle, fading ember in the sky. The colours of the afterglow change like the cooling hues of a sunset, shifting from energetic blues and violets down to reds, and then, eventually, disappearing into the dark. In the weeks following the burst, the afterglow continues its slow decay. What was once bright enough to spot with a backyard telescope becomes a target only large observatories can detect. Radio telescopes, in particular, might continue to pick up a whisper from the blast for many months. Even a year later, there can be a faint murmur in the radio spectrum as the shockwave travels ever outward, gradually dissipating into the cosmic background. This lingering afterglow paints a story of the burst's aftermath across the spectrum. It is as if the explosion, having cried out in gamma rays, now leaves an echo in softer lights that astronomers can study. By tracking the afterglow's evolution, how quickly it fades, and how its colors change, scientists learn about the environment around the burst and the mechanics of the jet. But beyond its scientific value, the afterglow is the universe's own memorial to the event. Long after the gamma ray flash is gone, a dim, ghostly light continues to glow, slowly fading and marking the spot of an incredible cosmic explosion. Even as the gamma ray burst was unleashed, another spectacular event was unfolding in parallel. The very star that produced those jets was also exploding outward in every direction. This is the star's supernova, the colossal detonation of its mass that accompanies the narrow jets. In the glare of the gamma ray burst, this supernova is initially hidden, like a brilliant performer waiting behind a curtain. But it is there, unfolding in the background, ready to take the stage as the gamma ray flash fades. The supernova is the broader, spherical explosion of the star's remaining material. When the core collapsed and the shockwave blew outward, it propelled most of the star's gas into space at tremendous speeds. In the first moments, that expanding fireball was overshadowed by the focused intensity of the jets. But as seconds turn to minutes and hours, the expanding debris field begins to shine in its own right. The result is a luminous cloud of ejected stellar matter, glowing as radioactive elements formed in the explosion decay and release energy. Within days, this supernova becomes a prominent spectacle, especially in visible light. Astronomers watching the afterglow of the burst will often notice a new surge of brightness a week or so later, the signature of the supernova revealing itself. What was a faint background presence now dominates the scene as the gamma ray and afterglow emissions diminish. This supernova is no ordinary star death either. It's among the most energetic of its kind, often termed a hypernova. Its light can continue to brighten and then fade over the course of weeks, outlasting even the afterglow of the jet. The connection between long gamma-ray bursts and these specific supernovae runs deep. Only certain kinds of massive stars produce this 1-2 punch of a focused gamma-ray beam and a sprawling supernova explosion. Typically, they are stars that have shed their outer layers before dying, so their supernova lacks hydrogen and shines with unusual intensity. The gamma-ray burst is like a piercing scream at the moment of death, while the supernova is the grand aftermath, a slower, symphonic explosion that follows the sharp burst. Together, they tell a complete story. The star's final moments in both narrow, blazing fury and expansive, fading glory. For the cosmos, this violent end is also a beginning of sorts. The supernova sprays the surrounding space with newly forged elements, oxygen, silicon, iron, and beyond, materials that will one day become part of new stars, planets, and perhaps life. Thus, even as it dies in unmatched fury, the star contributes to the ongoing cycle of cosmic evolution. In its demise, it seeds the universe with the ingredients for future worlds. These extraordinary explosions do not happen just anywhere. Long gamma-ray bursts have preferred cosmic neighborhoods. They are most often found in galaxies undergoing a frenzy of star birth, places where massive young stars are plentiful. In these galactic regions, new stars are forming in clusters and clouds, providing the raw fuel of future cosmic fireworks. The environments that breed gamma-ray bursts tend to be vibrant stellar nurseries. A closer look at the homes of these bursts reveals some common traits. Many long GRB host galaxies are relatively small or irregular in shape, often faint and blue with the light of young stars. In these galaxies, massive stars live fast and perish in spectacular ways, and gamma-ray bursts are one outcome of their demise. Additionally, these environments are frequently low in heavy elements. Astronomers call them metal poor. Such pristine conditions, reminiscent of earlier cosmic times, seem especially conducive to producing the kind of massive stars that spawn gamma-ray bursts. The low metal content in these regions plays an intriguing role. Heavy elements in a star can drive strong winds that blow away its mass and sap its rotation, but in metal-poor areas, even enormous stars can retain more of their mass and spin more rapidly throughout their short lives. This means that when they finally collapse, there is plenty of material and angular momentum to feed a central engine and form powerful jets. In essence, these simpler chemical environments allow the necessary conditions for a gamma-ray burst to arise from a dying star. As a result, long gamma-ray bursts often serve as beacons of cosmic youth. Many are observed in the distant universe, billions of light-years away, coming from epochs when galaxies were younger and heavy elements were scarcer. Even in the nearby universe, they tend to pop up in out-of-the-way galactic corners where fresh stars are still forming. By pinpointing these bursts, astronomers can map out pockets of vigorous star formation and primordial conditions. The most powerful stellar explosions seem to favor these less traveled corners of the cosmos, where massive stars can lead brief, brilliant lives unfettered by too many heavy elements. When these bursts go off, they not only tell the tale of a single star's death, but also illuminate the character of the galaxy that nurtured that star. Each burst carries with it a hint of the environment it came from, encoded in the afterglow and the faint whispers of light from its host galaxy. The light that reaches us from these cosmic explosions carries memories of what happened. Every flash and flicker, every color and wavelength, encodes clues about the burst and its origins. Astronomers act like detectives, examining the rays of light for subtle hints. In the spectrum of the afterglow, and in the timing of the burst's pulses, the dying star's secrets are whispered across space. By studying the light in detail, we can reconstruct aspects of the event that would otherwise remain hidden in the distant darkness. When scientists break apart the afterglow's light into a spectrum, a rainbow of its constituent wavelengths, they find the fingerprints of elements. As the afterglow shines through the gas of the host galaxy, it picks up absorption lines, dark bands that indicate the presence of certain atoms like carbon, oxygen, or iron. These telltale signs reveal the composition of the environment around the burst and of the star's own remnants. From them, one can discern whether the star was cocooned in its own expelled winds, or whether it lived in a primordial region untouched by many heavy elements. The spectrum also stretches toward the red end, shifted by the expansion of the universe, a clue that tells us how far away the event occurred, and thus how long ago in cosmic history the star's death took place. Sometimes the spectrum even reveals the products of the explosion itself. As the incandescent debris cools, it can imprint faint lines of elements, like nickel and cobalt, that were forged in the blast and are now decaying into iron. Such clues confirm that in the heart of the burst, new heavy elements were created, a bit of stellar alchemy captured from across the universe. Some of these bursts hail from the very young universe. Their light arrives after travelling for more than 10 billion years, making them among the most distant and ancient events we can observe. By catching such light, we are effectively looking back in time to an era when the first generations of stars were meeting their fiery ends. The timing of the light is another messenger. The gamma ray burst itself often flickers and flares with multiple spikes in brightness. The pattern of those spikes can hint at how the jet was powered. A smoothly fading afterglow might indicate one scenario, while an afterglow that suddenly brightens or levels off could suggest something extra at work, perhaps fresh energy injected by a magnetar engine. Sometimes, a plateau in the X-ray afterglow, a period when the light temporarily fades more slowly, whispers that a spinning magnetar is pouring additional energy into the afterglow before it finally settles. On the other hand, a rapidly dimming afterglow might hint that the central engine collapsed quickly into a black hole, cutting off the energy supply abruptly. Even the polarization of the light, the orientation of its electromagnetic waves, offers a clue. High polarization in the afterglow can indicate that the jet's light is strongly organized, perhaps beamed through narrow tunnels and filtered by magnetic fields. It suggests a structured jet, with magnetic forces shaping the flow of energy. Meanwhile, the very contrast between the burst's peak brightness and the afterglow's glow holds hints about how narrow the jet was and how much energy it carried. The sharper that contrast, the more tightly focused the explosion likely was. Each of these subtle pieces of information adds to the picture of what kind of engine lies at the center and how it drove the burst. In essence, the light from a gamma-ray burst is like a messenger traveling across the cosmos, carrying a record of catastrophe. When it finally reaches our telescopes, after perhaps billions of years in transit, that record can be read. Tiny details in the light, in its spectrum and its flickers and its polarization, are echoes of what happened in and around that dying star. Piece by piece, scientists decode these signals to understand the nature of the central engine that powered the burst, the conditions in the star's environment, and even the properties of the jet as it blasted through the star. The light remembers everything it has witnessed, and with careful observation, we too can share in that knowledge. The tale of gamma-ray bursts does not end with the death of lone giant stars. We have traced how a single massive star's swift life and violent demise can unleash a long-duration burst of gamma rays. Yet, in the cosmic tapestry, there is another thread that leads to a different kind of gamma-ray burst. These are flashes that are shorter, but no less potent. Swift storms of high-energy light born from a very different origin. Our journey now turns to explore this other side of the gamma-ray burst family. Unlike the long bursts that signal the death of a massive star, these other bursts arise from the deathly dance of two stellar remnants. Imagine two neutron stars, the dense cores left behind by earlier supernova, spiraling in toward each other over eons. When they finally collide, or when a neutron star merges with a black hole, the union releases a furious but brief explosion of gamma rays. These bursts last mere seconds or less, the blink of an eye compared to their long-duration cousins, and for that reason, they are called short gamma-ray bursts. Though fleeting, these short bursts pack incredible power, rivaling the energy of their longer counterparts, but unleashed in a much briefer tempest. Such cataclysmic mergers not only produce gamma rays, but also send out a burst of gravitational waves, ripples through spacetime, that humans can now detect with exquisitely sensitive instruments. These dual signals provide a new dimension to our understanding, marrying light and gravity to reveal a fuller picture of the event. The contrast between the two kinds of bursts is striking. Long bursts come from newborn black holes or magnetars in collapsing stars, often in far-flung cosmic nurseries. Short bursts, by contrast, come from ancient stellar remnants meeting their violent end, often in older, quieter regions of the universe. Indeed, observations show short bursts originating in galaxies that long ago ceased making new stars, places filled with old, evolved stellar populations. One is the scream of a single massive star's death. The other, the final spark of a binary pair that lived for billions of years. Yet both involve the formation of jets and the release of gamma radiation. Two different paths to similar kinds of cosmic fury. A common thread unites these phenomena despite their differences. Extreme gravity and violence that create narrow, relativistic jets. Whether tearing apart a massive star or merging ultra-dense stellar cores, the universe finds a way to unleash energy in focused torrents. In following this thread, we see how nature repeats a theme in different settings, channeling destruction into beams of light that can be seen across the cosmos. The story of gamma-ray bursts is thus a twofold tale, and understanding one side leads us naturally to investigate the other. Our exploration continues, and the next stage will carry us into those other cosmic catastrophes, the swift gamma-ray storms born from stellar unions. And so, we prepare to leave the realm of collapsing giants and step into a different cosmic drama. The stage that awaits is set not by youthful stars dying in glory, but by old remnants converging in a final embrace. The coming narrative will follow that connecting thread to these shorter bursts, brief flashes that carry their own mysteries and wonder. Our journey moves onward, from the ashes of single stars to the alchemy of colliding remnants, as we seek to unravel the secrets of the universe's ultimate explosions. It is a path that will lead us directly into the heart of those swifter storms, illuminating yet another aspect of the cosmos's grand design. Not every cosmic explosion begins with the death of a massive star. Far from the tumult of a massive star's final collapse, a quieter kind of cosmic powerhouse drifts in the darkness. It is small in size, but immense in weight, a star core crushed into something like a giant atomic nucleus. Imagine a sun's worth of mass squeezed into a sphere no wider than a city. This dense remnant is a neutron star, an ember left behind after a supernova has blown a star's outer layers away. This neutron star was once the heart of a giant star, perhaps 10 or 20 times the mass of our sun. For millions of years, that star fused elements in its core and shone brilliantly until its fuel was spent. In its final moments, the core collapsed under gravity's relentless pull, triggering a supernova explosion. What remained was that collapsed core itself, reborn as a neutron star. In the silent aftermath of such a blast, the core that remains is compact and incredibly heavy. It no longer shines like an ordinary star. Instead, it glows faintly with leftover heat as it slowly cools over eons, a hot cinder in the galactic night. The violence of the star's death is over, and what's left is an object of absolute stillness and extreme density, holding the memory of that cataclysm in every atom. In this shrunken star, matter has been pressed to extremes. A single teaspoon of its substance would outweigh the tallest mountain. It's as if all of Mount Everest's mass was somehow packed into a spoon in the palm of your hand. Beneath a neutron star's iron-hard crust lies a core where atoms themselves have been crushed. Electrons forced to merge with protons, creating a sphere made almost entirely of neutrons. Deep inside, the conditions are so extreme that scientists are not even certain what form matter takes. It might be a superfluid soup of subatomic particles, or perhaps even stranger states where neutrons break down into quarks. Understanding the true nature of a neutron star's core remains one of physics' great quests. The density here is beyond anything we encounter in daily life. We struggle to find comparisons that do it justice. Imagine a whole city's mass squashed into a grain of sand, or an entire planet's mass compressed into a ball the size of a small town. Even the Earth, if squeezed to neutron star density, would fit into a sphere only a few hundred meters across, a ball not much wider than a sports stadium. These analogies barely convey the reality, but they hint at how exotic and powerful this object is. Despite such overwhelming density and gravity, a lone neutron star is usually a quiet, unassuming body. It may spin rapidly. Some rotate dozens of times each second, and the fastest can whirl hundreds of times a second, a sphere spinning so fast it would blur to our eyes. If it has a strong magnetic field, it might send out beams of radiation as a pulsar, like a cosmic lighthouse sweeping the darkness. Even so, it remains more a cosmic lighthouse than a cosmic bomb. It is stable now, held up by quantum forces between neutrons that halt any further collapse. In the vast emptiness of space, it simply turns and drifts. To put it in perspective, an object that weighs a few pounds on Earth would weigh billions of pounds on a neutron star's surface. This tiny titan's gravitational pull is so intense that anything coming too close would be pulled in and smashed at almost light speed, with a force no human weapon could ever match. But in the deep vacuum where it floats, there is often little else around. A solitary neutron star might wander for millions or even billions of years without much incident, a compact ghost of a once brilliant sun. Astronomers suspect that our galaxy is sprinkled with millions of these dark stellar embers, though only a fraction are known. Most are invisible against the void, unless they send us a pulse, or the X-ray glow of infalling matter as a telltale sign of their presence. Sometimes, however, these city-sized suns are not alone. In rare but fateful cases, a neutron star has a companion, another star that also died and shrank into a dense remnant. Typically, such a pair begins life as two massive ordinary stars orbiting each other. One star explodes as a supernova first, leaving behind the first neutron star, while the second star continues to live. Later, the second follows suit, blowing off its outer layers and collapsing into a neutron star as well. The result is two neutron stars, born of a massive stellar sibling pair that remain bound together by gravity. Long after their parent stars have exploded and faded, the two neutron stars continue to orbit one another in a gravitational dance. They circle in the darkness like twin embers, each only a few tens of kilometers across, yet each containing more mass than our Sun. From a distance, you might not even notice them. They emit little visible light, maybe just a faint warmth, or a flicker of radio waves if one is a pulsar. In many ways they appear quiet and unremarkable, but the stage is set for an event far more dramatic than their silent existence suggests. For ages, nothing obvious changes in such a duet of stellar remnants. They revolve around a shared centre of gravity, two heavy points of darkness caught in each other's grip. The distance between them might initially be as great as the breadth of a planet, and at that range they circle slowly, perhaps taking many hours or days to complete one orbit. At first, it seems almost like a permanent stalemate. Each neutron star endlessly falls around the other, neither drawing noticeably closer in any time frame we could observe. The void around them is serene, with no gas or dust left from the long-ago supernovae to interfere or slow them down. It seems as though this dance could continue forever, unchanging, in the silent depths of space. But nothing lasts forever. Not even the most stately cosmic waltz. Over extraordinarily long spans of time, an invisible mechanism begins to tug at the dancers' feet, urging them closer together little by little. As the neutron stars orbit, they are not entirely isolated from the fabric of the universe. Their enormous masses and constant motion stir the space around them, sending out tiny ripples in space-time itself. These ripples carry away a minute amount of energy from the orbit with each passing cycle. In effect, the system leaks orbital energy into the universe in the form of gravitational waves, subtle vibrations of space that race outward at light speed. The effect is incredibly small, almost ghostly. At first, it is as if nothing is happening at all. But across millennia, millions, then billions of years, these minor losses slowly add up. The two stars draw imperceptibly closer with every revolution. Like a pair of ice skaters holding hands on a vast frozen lake, they spiral inward ever so gradually. Inch by inch, mile by mile, over hundreds of millions and then billions of years, the gap between the two neutron stars shrinks. A human observer would notice no change over a lifetime, or even over the entire span of human history. But over geological timescales, the difference becomes clear. Orbits that once took days now take hours, then minutes. The partners pick up speed as they come closer, their dance quickening from a languid waltz to a brisk foxtrot. Eventually, after an almost unimaginable duration, perhaps longer than the current age of our Sun, the two dense stars might be orbiting each other in mere seconds. At first, centuries and millennia pass, with barely a hint of change. But as time marches on, the partners whirl faster and faster, and the more energy their dance bleeds into space as gravitational waves. By the time their separation has closed to something comparable to the size of a large city, their dance is no longer stately. It has become a dizzying blur. Each neutron star now hurtles around the other many times per second. They have come a long way from their initial slow embrace. What began as a measured, near-eternal circling has transformed into a frantic orbit. Space itself quivers ever so slightly from their motion. The gravitational ripples they send out grow from faint whispers to a louder chorus on the cosmic stage, a song that only very sensitive instruments would hear as it washes over distant worlds. Astronomers actually confirmed this slow dance and gradual tightening long before we ever witnessed a neutron-star collision directly. In the late 20th century, a pair of neutron stars, a binary pulsar, was discovered in our galaxy, and careful measurements showed that their orbit was shrinking by a tiny amount each year. It was the first solid evidence of energy being carried away by gravitational waves, exactly as Einstein's theory had predicted. This achievement was so significant that the astronomers who discovered this binary pulsar were awarded the Nobel Prize, since it confirmed gravitational waves were real long before we could directly detect them. Through those observations, scientists knew that given enough time, even the most stable-looking binary stars would eventually spiral together. Some pairs might take longer than the current age of the universe to collide, but others are destined to meet sooner. In the case of that particular pair, calculations showed they would merge in about 300 million years. The clock of their cosmic dance is slowly winding down, as is the case for many such systems throughout the universe. Inexorably, the force of gravity, through the slow leakage of orbital energy, drives the two neutron stars towards their fate, setting the stage for a final act, billions of years in the making. In the last few seconds before the final merger, the frequency of the star's orbit rises into a thrilling crescendo. What began as a slow dance has become a wild, whirling spiral. If we could somehow convert the gravitational waves into sound, we might hear a rising tone, a kind of cosmic chirp, as the stars swing around each other faster and faster. Each passing moment, the pitch would climb and the tempo quicken. This is gravity's siren song, announcing that the finale is near. The very fabric of space around the stars is ringing with anticipation, like a drum skin vibrating under an accelerating drum roll. The two neutron stars, after an almost eternal courtship, are now on the verge of becoming one. Each fraction of a second, the distance between the two stars narrows further. By now, each dense sphere is moving at an incredible speed, a significant fraction of the speed of light. They whip around each other hundreds of times in what amounts to the blink of an eye. Tidal forces stretch and distort their ultra-dense crusts, tugging on each star like taffy. For a brief moment, the two neutron stars might even resemble teardrops, rather than perfect spheres, each elongated toward the other by their mutual gravity. Space-time itself is being twisted and shaken by this furious motion. Wave after wave of gravitational energy rolls outward in rapid succession, carrying away the last reserves of orbital energy. In these final moments, the system is invisible in ordinary light. There are no bright flares yet, no obvious sparks to see, but it shines brilliantly in the domain of gravity. If one had a way to see gravitational waves, this merging binary would be a beacon flashing and wailing its impending catastrophe to the cosmos. These final orbits happen almost unbelievably quickly. In the last second or two, the stars whirl around each other dozens, then hundreds of times as they close the remaining gap. What was once a slow gravitational whisper is now a roaring rush of energy, though only in those ripples of gravity that race outward across the universe. The amplitude of the gravitational waves soars. Space-time is being flexed more intensely than ever by these two objects. Incredibly, at the peak of this final dance, the energy being carried away by gravitational waves is staggeringly high. For a brief moment, it can exceed the luminosity of all the stars in an entire galaxy, though virtually none of that energy interacts with matter. It's dissipated through the warping of space itself, invisible except to instruments attuned to these subtle distortions. All the while, to any distant onlooker with regular telescopes, nothing visible has yet betrayed the drama. Only a special kind of observatory, the gravitational wave detectors on Earth, would sense the growing frenzy, as the very fabric of space-time itself vibrates with the impending climax. At last, the two neutron stars can no longer remain apart. Their spiraling dance brings them so close that nothing can prevent their collision. They are mere neutron star diameters from each other and closing in rapidly. In these final milliseconds, the gravitational waves reach a fever pitch and then suddenly stop, a telling silence following the cosmic crescendo. The universe itself seems to hold its breath as the two objects, each the mass of a sun, prepare to collide. After billions of years of quiet orbit, their moment of union is about to arrive. And then, the long build-up comes to an abrupt end. In the space of a heartbeat, the two neutron stars collide and merge. At that instant, a cataclysmic transformation occurs. All the energy pent up in their spiraling dance, all the mass and momentum, is suddenly released in one final, violent blast. The two objects crush into each other and form one extremely compact remnant. It could be a single, overlarge neutron star for a brief moment, or it might collapse immediately into a newborn black hole. Either way, the collision unleashes a surge of energy that had been locked away in their orbit and dense matter. A fierce blast of subatomic particles, including an intense flood of neutrinos, those nearly massless ghost particles, erupts from the merging wreckage, carrying away a significant portion of the energy. In a tiny fraction of a second, twin jets of ultra-fast particles and radiation are blasted out from the poles of the new merged object. These jets tunnel their way through whatever debris remains and shock the surrounding space. A flash of high-energy gamma radiation is unleashed, beaming out into the universe. This flash is a gamma-ray burst, an extremely intense but fleeting pulse of light, born from the violence of two city-sized suns becoming one. The gamma-ray burst that results is startlingly short. It passes in under 2 seconds, sometimes in just a few tenths of a second. One moment, space is dark and silent. The next, it is flooded with the highest energy light, and then almost immediately it falls dark again. It is as if a camera flash has illuminated a vast dark room for an instant, and then vanished. These are the short gamma-ray bursts, briefer than a single breath, as quick as the blink of an eye, yet incredibly powerful. In that split second of fury, the burst releases more energy than millions of stars would emit in years. To put it another way, one of these brief bursts can outshine the sun so utterly that it emits in 1 second what our sun will take its entire 10 billion year lifetime to radiate. For that moment, the merging neutron stars outshine entire galaxies in gamma rays. Instruments on distant spacecraft, designed to watch for precisely such events, register this sudden spike of gamma radiation and alert astronomers that somewhere in the cosmos, 2 neutron stars have met their dramatic end. Short gamma-ray bursts truly live up to their name. They don't linger at all. This fleeting blast stands in stark contrast to the long-lasting gamma-ray bursts that come from collapsing giant stars. Those long bursts can play out over tens or even hundreds of seconds, sometimes pulsing and flickering as the massive star's core falls apart and powers a sustained eruption. A long burst is often accompanied by the brilliant bloom of a supernova explosion, the dying star's grand farewell that can remain bright for weeks. But here, with colliding neutron stars, there is no such spectacle of a giant star tearing itself to pieces. No supernova accompanies this flash, because the progenitors were not enormous living stars at the end of their lives. They were the dense corpses of stars, long dead. The short burst is over almost as soon as it begins, with no prolonged engine to feed it. The power source here is the sudden formation of a compact remnant and the ultra-fast jets that race out. Once those jets have expelled their burst of gamma rays, the intense flash fades. There is no extended afterfire of a collapsing star, just a brief blaze, and then a return to quiet darkness. Yet even though the gamma flash itself vanishes in an instant, the story of this merger is not finished. The violent collision has flung out a spray of neutron-rich debris, and in the hours and days following the burst, that debris will give rise to a very different kind of glow. For now, immediately after the burst, that ejected material is extremely hot, but mostly invisible. A cloud of exotic matter expanding rapidly into space. The region around the merger briefly returns to an eerie calm, but only temporarily. In the darkness where 2 neutron stars have now become one object, a hypermassive neutron star or nascent black hole, shreds of neutron star material are flying outward. Though this aftermath is dim compared to the gamma flash, it holds profound significance. As this cloud of expelled matter begins to cool and undergo nuclear reactions, it will start to shine in its own subtle way. A faint glow will emerge, revealing the fingerprints of new elements forged in the heat of the merger. The next act of this cosmic event is about to unfold, a transformation of initial violence into a gentler afterglow that astronomers can study long after the gamma rays have faded. In the days following the merger, what was initially invisible to human eyes transforms into a source of faint but telling light. The expanding cloud of stellar debris that was flung out at the moment of collision begins to shine as it cools and changes. As this cloud thins and its atoms recombine into new configurations, it releases energy in a softer glow across multiple wavelengths. At first, this afterglow may appear bluish or ultraviolet, the mark of an extremely hot, rapidly expanding cloud dominated by lighter elements. But as hours and then a day or two pass, the color of the light shifts. The glow becomes more golden, then reddish. This happens because heavier elements are starting to dominate the mix, and those heavier elements cast a redder hue on the cooling fireball. Astronomers call this transient glow a kilonova. The term nova means new star, historically used when a new star-like point of light would appear in the sky. The prefix kilo implies 1,000, indicating that this phenomenon is roughly 1,000 times brighter than a typical classical nova, which occurs when a white dwarf star flares up. A kilonova is still much dimmer than a titanic supernova from a collapsing star, but it's bright enough to be detected across vast distances. To someone watching with a powerful telescope, it's as if a new, faint star has blossomed at the merger's location, one that glows in blue tones for a short time, then fades to red, before gradually disappearing over a week or two. Within that expanding debris cloud, an astonishing kind of alchemy is taking place. The neutron-rich matter hurled out by the merger is the perfect breeding ground for some of the heaviest elements in the universe. In the intense conditions of the aftermath, atomic nuclei greedily capture neutrons and then undergo radioactive decay, transforming into new, heavier elements. In a very real sense, the collision of two neutron stars is a cosmic forge. It's here that elements like gold, platinum, uranium, and many others heavier than iron are crafted. The quantities are staggering to contemplate. A single neutron star merger can synthesize an amount of gold comparable to several times the mass of the Earth, along with even larger masses of platinum and other heavy elements. Ordinary stars cannot produce these elements in significant quantities. They require the extreme flood of neutrons that only events like this can provide. As the debris cloud expands and cools, these newborn atoms settle into more stable forms, and their radioactive decays heat the cloud from within, causing it to glow. The light we detect from a kilonova carries the fingerprints of those heavy elements, a spectral signature of freshly forged gold and dozens of other new atoms spreading out into space. Think about this. The gold in a wedding ring, or the platinum in an electronic device, was likely formed in a neutron star merger that occurred billions of years ago. Long before Earth existed, a kilonova enriched its surrounding region of the galaxy with glittering new elements. Over eons, that enriched gas mixed with other cosmic clouds and eventually became part of new stars and planets. Our own solar system, our own planet, carries the remnants of countless such cosmic forges. The jewelry on our fingers and the precious metals in our technology are, in a way, souvenirs of one of the most violent acts of cosmic creation. It's a poetic union of destruction and creation on a grand scale. The universe turning catastrophe into opportunity, forging beauty and utility from the ashes of stellar death. The kilonova's light reaches its peak brightness over a few days and then gradually diminishes. To the naked eye, even if such an event occurred in a nearby galaxy, it would appear only as a faint pinprick of light, and in most cases they are, far too distant to be seen without powerful telescopes. But through telescopes and sensitive instruments, observers can track its evolution in detail. In 2017, astronomers around the world did exactly that when gravitational wave detectors announced a neutron star merger in a galaxy 130 million light-years away. Telescopes swiftly zeroed in on the merger's region, and sure enough, a brand new point of light was found. In the first couple of days, it shone a bright bluish color, consistent with the formation of some lighter heavy elements. After about a week, it had faded significantly, and its light had shifted to a deep red hue, indicating the presence of very heavy, rare earth elements, lanthanides, in the expanding cloud. This was the kilonova we had long hoped to observe, captured in exquisite detail for the first time. The observations were a triumph, confirming that neutron star crashes do indeed produce kilonovae and manufacture precious elements. Theorists had predicted it for years. Now the sky itself was showing us the truth unfolding in real time. Such afterglows are gentle, in contrast to the ferocity of the initial gamma-ray burst. But they are profoundly informative. By studying the light from a kilonova, scientists can decipher the chemical composition of the debris, reading the spectral lines of newly formed elements as one might read the lines of a cosmic recipe. Each kilonova we observe is like witnessing the universe's workshop in action, revealing how and where the elements of the periodic table are made. It is a beautiful coda to the violent merger. After the flash of gamma rays comes a quieter bloom of multicolored light, telling the story of creation amid destruction. Eventually, as weeks and months pass, the kilonova's glow fades completely. The site of the merger returns to darkness, invisible light, at least, now marked only by whatever compact remnant was left behind, and an expanding cloud of matter that will gradually disperse into the surrounding space. But the legacy of that single event will endure in the newly minted atoms it scattered, atoms that will drift through interstellar space, perhaps to become part of new stars, new planets, or even new life in the distant future. In the aftermath of chaos, the universe has crafted fresh building blocks, enriching itself for the ages to come. Quiet outskirts and ancient homes. These are indeed the places where short gamma-ray bursts often prefer to appear. When astronomers trace the location of a short GRB, they frequently find it originated in the edge of a galaxy, or in a galaxy that itself is old and tranquil. Picture a massive elliptical galaxy, a giant, rounded swarm of stars that stopped forming new suns long ago. Its stars are ancient, many billions of years old, and they shine with a soft, reddish light. In such a galaxy, there are no bright nebulae or blue young star clusters, just a broad, gentle glow of aging stars. Now imagine, out in the outskirts of this peaceful realm, a sudden flash of gamma rays erupts. It's a brief blaze in a settled, elderly neighborhood of the cosmos. This is a typical setting for a short gamma-ray burst. Unlike the long bursts, which tend to announce themselves amid galaxies full of young, massive stars and vigorous star formation, the short bursts show up in far quieter surroundings, more akin to cosmic retirement homes than cosmic nurseries. This tendency was an important clue to the nature of short GRBs. Early on, when researchers looked for the aftermaths of short bursts, they often found little or no sign of star-forming activity. There were no bright young stars or obvious supernova remnants near the burst locations. Instead, one might find an inconspicuous, reddish galaxy, or an environment seemingly devoid of notable features. In fact, a significant fraction of well-studied short bursts have no identifiable host galaxy at all, even with our most sensitive telescopes. At first, that was perplexing. How could a tremendous explosion occur in what looked like the middle of nowhere? But the likely explanation lies in the history of the neutron stars themselves. When each neutron star's progenitor went supernova long ago, the explosions may have given the neutron stars a powerful kick, like cannonballs being blasted from a cannon. A neutron star pair could have been launched on a long voyage, moving at hundreds of kilometers per second. Over millions of years, such a binary could drift tens or even hundreds of thousands of light years away from its birthplace. By the time the two neutron stars finally merged, they might be far outside their original galaxy's bright core, or even flung entirely into intergalactic space. So when their burst signal reaches our telescopes, we see a flash, seemingly coming from the middle of nowhere. This scenario explains why short GRBs can appear in such apparently empty locations, or in the dim halos of galaxies rather than their bustling centers. The universe had set these neutron star mergers on a slow fuse. The stars that created them lived and died in a youthful galaxy, bursting with activity. But the remnants they left behind took their time, sometimes billions of years, before detonating as a gamma-ray burst. By then, the galaxy had aged and quieted, or the remnants had wandered far afield. The short burst arrives like an echo from a bygone era, finally releasing its energy in a much quieter cosmic setting. The contrast with long gamma-ray bursts is stark. A long burst, produced by the catastrophic death of a massive star, almost never hides its origins. It's usually found in a bright patch of a galaxy teeming with star formation, perhaps in a blue spiral arm, or in a tiny dwarf galaxy boiling with new stars. A short burst, by contrast, might come from the smooth, diffuse outskirts of a large galaxy, or from an old elliptical galaxy, where hardly any new stars have been born in billions of years. One way to think of it is, long bursts are like fireworks at a lively cosmic festival, whereas short bursts are like a solitary spark in a deserted field at night. Neither type is any less powerful in itself, but the backdrop against which they occur is vastly different. This difference in environment was one of the big hints that short bursts originate from an older population of sources, namely merging neutron stars, rather than the death of a single young giant star. In these calmer galactic neighborhoods, when a short GRB goes off, it momentarily lights up the darkness and then fades, leaving behind only subtle clues. Aside from the gamma flash, and perhaps a faint afterglow or kilonova, which can be challenging to detect across billions of light years, there might be no lasting trace of the event. The galaxy, if one is even present, soon returns to its quiet routine as though nothing happened. Only through diligent detective work, searching for faint glimmers of a host galaxy, or sifting through the subtle colours of any afterglow, do astronomers piece together the evidence of what took place. Each time a short burst is pinpointed to such a quiescent locale, it reinforces the narrative. These explosions come from aging stellar relics, finally meeting their end, often far from the youthful chaos that originally birthed them. However, not every brief burst of gamma rays in the universe heralds the merger of neutron stars. For years, astronomers puzzled over a few fast gamma-ray flashes that were just as sudden and short-lived as the expected merger bursts, yet their locations and properties didn't quite fit the pattern. The investigation eventually pointed to a very different culprit: the tantrums of a magnetar. A magnetar is a neutron star with an ultra-powerful magnetic field, the most intense magnetic fields known in the cosmos. How strong are they? Imagine a magnetic field so mighty that it could erase credit cards from tens of thousands of miles away, or distort the very structure of atoms. A magnet's field is on the order of 1 trillion times stronger than Earth's magnetic field. With such tremendous forces permeating its interior and crust, a magnetar is prone to occasional violence. Sometimes the magnetic field inside it becomes unstable and suddenly reconfigures itself, releasing a huge amount of energy. When that happens, the rigid crust of the neutron star cracks and shifts in what is effectively a starquake. In a flash, the magnetar unleashes a torrent of high-energy radiation. We call this event a giant flare. It's as though an enormous store of magnetic energy, built up within the star over years or decades, snaps free all at once. For a brief moment, a magnetar flare can rival the brightness of a gamma-ray burst. In fact, one of the brightest gamma-ray events ever recorded by our instruments was not from a distant galaxy at all, but from a magnetar right here in the Milky Way. Astronomers remember that event vividly. In late 2004, a sudden blast of gamma rays and X-rays arrived that was so intense it saturated detectors and even made Earth's upper atmosphere reverberate with a surge of ionization. It turned out to come from a magnetar about 50,000 light-years away. For a fraction of a second, that magnetar flare outshone almost everything else in the gamma-ray sky. If we hadn't determined its distance, we might have assumed such a powerful flash came from halfway across the universe. Instead, it was a star in our own galactic neighborhood, a magnetar releasing a colossal burst of energy in a fit of magnetic upheaval. Magnetar flares tend to have distinctive signatures that set them apart from true cosmic gamma-ray bursts. The initial blast of gamma rays can be extremely intense, but it's usually followed by a steadily fading tail of X-rays and gamma rays that can last for minutes. That tail often shows pulsations or flickers corresponding to the magnetar's rotation period or seismic vibrations, essentially the star ringing like a bell after the quake. For example, the Great 2004 flare exhibited an X-ray afterglow that pulsed with a regular period, the spin period of the magnetar, and decayed over a few minutes. Such behavior is not expected from a neutron-star merger. Those are over too quickly to produce a long tail with pulsations. Another key difference is location. A genuine short GRB typically comes from a faraway galaxy, millions or billions of light-years distant, outside our Milky Way. A magnetar flare, on the other hand, originates within our galaxy, or in a nearby satellite galaxy. So if a short gamma flash is found to be extremely bright, and yet its source is very close by on cosmic scales, or if its gamma-ray profile shows that telltale pattern of an initial spike followed by a ringing tail, scientists suspect it's a magnetar giant flare rather than a neutron-star merger. In those cases, we don't expect to find a kilonova afterglow or a gravitational wave signal, as we would with a merger. Instead, we might locate a known magnetar at that position, or detect the characteristic spin period of a magnetar in follow-up X-ray observations. Astronomers have become adept at telling these masquerades apart from the genuine merger-driven bursts. Catalogues of known magnetars and their past flares are constantly checked against new gamma-ray burst observations. When a short gamma-ray flash is detected, one of the first things scientists do is see whether its sky position lines up with any known magnetar. If a burst appears extraordinarily bright, yet originates from a direction in or near our galaxy, or if the gamma-ray light curve shows that familiar spike and tail pattern, alarm bells go off. This is likely a magnetar in our cosmic backyard, not a distant collision. By combining all the clues, the shape of the gamma-ray signal, the presence or absence of afterglow, the estimated distance, researchers can usually distinguish an imposter magnetar flare from a true cosmic merger event. It's a testament to nature's inventiveness that two very different phenomena can produce such similar bursts of high-energy light. One is the catastrophic union of two orbiting stellar remnants. The other is a sudden magnetic temper tantrum of a single, highly magnetized star. In both cases, we get a flash of gamma rays that might last only a heartbeat. But understanding the context is crucial. Thanks to careful observation and cross-checking, what once caused confusion can now be categorized correctly. Giant magnetar flares remain fascinating. They are among the most violent events that can happen to an isolated neutron star. But they are a different chapter of the cosmic story than the gamma-ray bursts born of mergers. These flares are rare cosmic tantrums. Only a few such giant magnetar flares have been recorded in our galaxy in the past few decades. By recognizing these masquerades, astronomers ensure that the true short GRBs, the merger kind, are identified correctly, and that we don't mix apples and oranges in our quest to understand the universe's most powerful explosions. Even among the genuine merger-driven bursts, nature has more than one way to stage the event. The classic scenario we've focused on is two neutron stars merging with each other. But there is another dramatic possibility: a neutron star merging with a black hole. In cosmic terms, this is a union of unequals. One partner is a dense stellar remnant, the other is an even denser abyss from which not even light can escape. Astronomers suspect that such mixed pairs exist and occasionally merge, producing short gamma-ray bursts of their own. But how would that differ from the merger of two neutron stars? When a neutron star spirals into a black hole, much depends on the black hole's characteristics, primarily its mass and its spin. If the black hole is very massive compared to the neutron star, its gravity might completely overwhelm the neutron star without shredding it first. In such a case, the neutron star could be swallowed whole in one gulp, so to speak, without leaving much debris outside the black hole. If that happens, there may be little or no material left to form the hot, glowing accretion disk and jets that produce a gamma-ray burst. The merger would still release a tremendous amount of energy in gravitational waves. Space would ring with the signal of a neutron star plunging into a black hole, but it might produce no flash of light at all, or only a very faint one. To an observer on Earth, that event might pass unnoticed by our telescopes, but a gravitational wave observatory would quietly record the telltale chirp of the merger in spacetime. On the other hand, if the black hole is smaller, say only a few times the neutron star's mass, or if it's spinning rapidly, the encounter can play out quite differently. The tidal forces from the black hole could tear the neutron star apart before swallowing it. In that scenario, a large amount of neutron-rich matter suddenly gets yanked into an orbit around the black hole, forming a heated, whirling accretion disk. That disk can launch jets of matter and energy at near light speed along the black hole's poles, just as we believe happens in neutron star pairs. Those jets would produce a short gamma-ray burst, very similar to the neutron star case. Additionally, some fraction of the neutron star's matter could be flung out into space during this violent process, which means a kilonova could also result, shining with freshly minted heavy elements, albeit potentially less massive or bright than in a two-neutron star merger. In essence, a neutron star black hole merger is a kind of hybrid event. Part of it resembles a neutron star merger, if the neutron star gets torn apart, and part of it behaves like a black hole feeding on a star. Detecting these in the wild can be tricky, because the outcomes can vary, from a full-blown gamma-ray burst to almost no electromagnetic signal at all. It's possible that many neutron star black hole collisions have happened that we simply didn't notice with traditional telescopes. We might know about them only through their gravitational wave signals, which don't depend on light. Indeed, in recent years, gravitational wave observatories have picked up a couple of events that appear to be exactly this kind of merger: one neutron star and one black hole. In those instances, telescopes scoured the predicted locations of the mergers for any glow or burst of gamma rays and found nothing conclusive. This suggests those black holes may have swallowed their neutron star companions almost silently, leaving us with only the sound of spacetime to know the event happened. Conversely, astronomers have also identified short gamma ray bursts that might be linked to neutron star black hole mergers. These are cases where a burst was observed, and later an analysis of gravitational wave data hinted that one of the collision partners had the mass of a black hole and the other a neutron star. As gravitational wave detectors improve and more events are observed, we expect to paint a clearer picture of how common each scenario is and how to tell them apart. Each new detection will help us understand whether a burst was the product of two neutron stars or a mismatched pair. What's remarkable is that, through gravitational waves, we can know when a black hole is involved, even if our telescopes see nothing. The song of the merger, captured in gravitational waves, carries information about the masses of the objects. A collision of two neutron stars produces a slightly different gravitational melody than a collision of a neutron star and a heavier black hole. The waveform encodes the signs of an asymmetric pairing. Thus, even an apparently dark merger, one with no light, can be recognized and understood by its gravitational signature. This synergy of light and gravitational observations is giving us a far more complete understanding of short gamma-ray burst sources. Whether the final cosmic dance is between two equal partners or an uneven pair, we are learning to recognize each step of their choreography through multiple channels of perception. And so, in the era we live in, light is no longer our only courier of cosmic news. A whole web of signals now interweaves to tell the complete story of dramatic events like neutron star mergers. Gamma rays provide the first shout, swift and piercing. Then come other forms of light: X-rays, visible light, infrared, radio waves, each arriving on its own schedule, each carrying a different piece of the story about the aftermath. Alongside all of these travels, an entirely different kind of signal: gravitational waves, ripples in space-time itself. Now that we can detect both kinds of messengers, light and gravity, we humans have, for the first time, truly seen and heard a cosmic event unfold. This new era of listening actually began a couple of years earlier. In 2015, scientists detected gravitational waves directly for the very first time, catching the merger of two black holes in a distant galaxy. That historic discovery proved that we could hear the universe, confirming Einstein's century-old prediction of those waves. However, that black hole collision came and went in utter darkness. Two black holes merging emit no light, so only the gravitational waves signaled their presence. It was a groundbreaking moment for physics, but it lacked any accompanying glow for telescopes to capture. The stage was set, then, for an even more illuminating demonstration of this multi-messenger power, a collision that would be both heard and seen. This became strikingly clear on an August day in 2017. At gravitational wave observatories on Earth, lasers quietly monitoring for space-time tremors suddenly sensed the distinctive chirp of a binary neutron star in spiral. Just 2 seconds later, a space telescope picked up a short burst of gamma rays from the very same patch of sky. It was an astonishing cosmic coincidence, Two completely different observatories catching different aspects of the same event almost simultaneously. Alerts went out worldwide. In moments, astronomers everywhere knew that something monumental was unfolding. Dozens of telescopes, both in space and on the ground, swung into action, aiming at the coordinates provided. Within about half a day, a new, faint pinpoint of light was discovered in the galaxy NGC 4993, 130 million light-years from Earth. Over the following nights and weeks, that point of light was closely watched. It was the telltale kilonova, the afterglow of a neutron-star merger, changing color exactly as predicted, from an initial bluish glow to a reddish hue in the days after. The host galaxy, NGC 4993, turned out to be a large, ancient elliptical galaxy with no recent star formation. Precisely the kind of environment we expected for a neutron-star merger. Everything about the observation clicked together like pieces of a cosmic jigsaw puzzle. This event, now known by the identifier GW170817, was a Rosetta Stone for astronomers. For the first time, they had both the text of gravitational waves and the translation provided by electromagnetic light across the spectrum for a neutron-star collision. From the gravitational wave signal, scientists determined that two objects, about 1.4 times the Sun's mass, each had spiraled together, confirming they were neutron stars. That signal also carried clues about the final moments of the inspiral, helping constrain the properties of ultra-dense matter. Meanwhile, the short gamma-ray burst told us that jets had indeed formed and that Earth was fortunately aligned to catch a bit of that gamma flash. Interestingly, the gamma burst was weaker than a typical short GRB, likely because the jet was not pointed directly at us, but slightly off-axis. The optical and infrared glow of the kilonova revealed the creation of heavy elements. By analyzing its spectrum, scientists identified signatures consistent with freshly forged gold and other heavy atoms radiating as they decayed. X-ray and radio telescopes, joining the effort days to weeks later, observed a faint afterglow that helped confirm the presence of expanding jets and how they interacted with the surrounding interstellar medium. It was as if a story that had long been told in whispers suddenly boomed forth in full stereo sound. Each type of signal complemented the others. The gravitational waves provided a detailed chronicle of the motion and masses leading up to the merger. The gamma rays gave the dramatic opening flash of the merger itself. The kilonova's light filled in the rich aftermath, showing us the newly formed elements and the behavior of the ejected material. No longer were we left to puzzle over a flash of light with no context. We had context in abundance. This marked the dawn of what scientists call multi-messenger astronomy, the practice of observing the universe through fundamentally different carriers of information. It's akin to watching a silent movie for decades and then suddenly getting sound. Now the orchestra plays alongside the visuals, and the cosmic performance comes alive in a new way. The result of this first multi-messenger observation was profound. It confirmed decades of theory. Yes, short gamma-ray bursts are indeed caused by merging neutron stars. Yes, those mergers produce heavy elements. Yes, gravitational waves from such events can be detected, and they bring entirely new information that light alone could never provide. It was a triumph of both technology and human collaboration. Thousands of scientists and hundreds of instruments, all tuned in to a single cosmic event. It also cemented the idea that to truly understand what's happening out there, we benefit enormously from catching every messenger we can. Since that watershed moment, whenever a gravitational wave detector senses a possible neutron-star merger, an alert is broadcast immediately to astronomers worldwide. Something's happening. Point your telescopes here. Likewise, if a short gamma-ray burst is detected by satellites, teams promptly check gravitational wave data to see if a simultaneous ripple in spacetime was caught. We now have a network of eyes and ears on the cosmos, working in unison. Each new event, observed with multiple messengers, further enriches our understanding. We've already learned, for example, that not every neutron-star merger will yield a detectable gamma burst. Sometimes the jets are misaligned, or the neutron star gets swallowed quietly. We've also found that gravitational wave detectors can uncover mergers that our telescopes might miss entirely, and vice versa. This complementary strength means our net for catching cosmic phenomena has widened significantly. The tapestry of information from combined signals gives us confidence and clarity. Before 2017, we had indirect evidence that neutron star mergers were factories for the heaviest elements. Now we've directly watched one at work. Before, we suspected that some short GRBs might be neutron star black hole mergers or off-axis events. Now we can confirm a merger happened even if the gamma signal was faint or absent. Each piece of this multi-messenger puzzle sharpens the whole picture. Indeed, the universe communicates in many forms, and at last we are listening in multiple channels. No longer do we rely on light alone. We've welcomed gravitational waves as equally important messengers. The story of gamma-ray bursts, the universe's ultimate explosions, has become a rich narrative told by different voices of physics. It's reminiscent of watching a thunderstorm. For a long time we only saw the lightning, but now we can also hear the thunder. Separately, each sense told part of the story. Together, we get a fuller sense of the power and grandeur of the event. In the case of a neutron-star collision, we see the lightning in the gamma-ray flash and its afterglow, and we hear the thunder in the gravitational waves that shake the fabric of space. When both sight and sound reach us, our awe deepens and our knowledge expands. With this new ability to capture multiple signals, humanity has effectively widened its way of listening to the cosmos. We have built observatories that go beyond just seeing. We now have ears sensitive to the tremors of space-time and eyes covering all wavelengths of light. And we've learned how to respond when the sky speaks. The instant something noteworthy happens out there, whether space itself rings or a sudden burst of light arrives, alerts spread across the globe at the speed of the internet. In a very real sense, the astronomers of Earth have become a team of cosmic first responders, always on call. The coordination is unprecedented. When a gravitational wave signal rolls through the Earth, automated systems at observatories like LIGO and Virgo immediately recognize it and broadcast a notice. A potential cosmic merger has been detected, roughly in such and such direction. In response, telescopes on every continent and in orbit swivel toward that patch of sky. Observatory schedules are interrupted without hesitation. Whatever those telescopes were observing minutes before is quickly set aside, because the universe has announced an event. Similarly, if a gamma-ray satellite detects a burst, an alert goes out and gravitational wave data are combed for any concurrent signal. It's a beautifully choreographed dance between technology and human collaboration. We have essentially networked our planet's observatories into one grand instrument, poised to catch the faintest whisper or the loudest shout from the cosmos. This vigilance has changed our relationship with the night sky. There's a newfound intimacy in how we engage with the universe. We no longer merely gaze at the stars in passive wonder. We are actively listening and even feeling the subtle vibrations of distant cataclysms. It's as if, after centuries of watching cosmic fireworks from behind soundproof glass, we've finally opened a door and can hear the cosmic symphony. Each gravitational wave detection is like a gentle handshake from across the void, a direct physical connection to events in far-off galaxies. Each electromagnetic observation is the light reaching our eyes from those same events. With both together, we attain a much fuller sensory experience of phenomena that are, by their nature, far beyond the realm of everyday human experience. As our cosmic senses have expanded, so too has our sense of presence in the universe. We often talk about hearing gravitational waves, and while it's a metaphor, there's truth in it. Scientists sometimes convert the wave data into sound, allowing us to literally listen to the chirps of colliding stars on a speaker. It's an awe-inspiring sound, a faint rising whoop that represents two incredibly dense objects finally coming together. These are the songs of the cosmos, once entirely silent to us, and now audible with the right instruments. To be privy to such things feels like a gift, a direct communication from places we will never be able to touch, except through these messengers. We have entered an era where the universe's most elusive secrets are becoming shared knowledge, thanks to this multi-messenger approach. And this is only the beginning. In the coming years, even more sensitive gravitational wave detectors will join the network, improving our hearing and extending it to fainter, more distant events. Plans are underway for new facilities on the ground and in space that will listen for these waves from collisions involving black holes, neutron stars, and perhaps events we have yet to imagine. In Japan and India, new gravitational wave observatories are being built to join the network, and a space-based detector called LISA is on the drawing board for the 2030s. Each will extend our ability to detect these cosmic whispers, ensuring we catch even more of the universe's faint murmurings. Likewise, next-generation telescopes, far more powerful than any before, are coming online to deepen our vision, ready to capture the faintest afterglows or the swiftest flashes. We are sharpening all our senses in concert, preparing for whatever cosmic phenomena nature will reveal next. With our widened listening and watching, we stand ready for the sky's next message. The moment the universe whispers of an event, perhaps through a subtle tremor in spacetime or a sudden burst of high-energy light, we respond. It's a poetic dance of alertness. The sky speaks, and humanity listens together. There's a poetic elegance in this new mode of astronomy. It feels as though we are slowly weaving ourselves into the cosmic narrative, not as passive observers, but as engaged listeners and participants. Each time the universe says something through these events, we answer with curiosity and action. We capture the signals, we analyze their meaning, and we refine our understanding of the cosmos. It's a one-sided conversation, perhaps, but deeply meaningful. The cosmos speaks in the language of physics, and we reply by deciphering its messages and sharing the story they tell. Amid this interplay of destruction and discovery, there is also a philosophical reflection to be made. The most violent cosmic events we observe are not just wild fireworks in the void. They are creators as well as destroyers. From the death throes of stars come the seeds of new beginnings. The gold and other heavy elements, forged in neutron star mergers, eventually find their way into the clouds of gas and dust that form new stars and planets. In fact, our own Earth is rich with elements that were fashioned in such cosmic furnaces long before the sun was born. Without those ingredients, planets like ours, and life itself, might not exist. Thus, when we listen to a gamma ray burst or watch a kilonova's glow, we are, in a sense, witnessing the universe in the act of recycling matter and sowing the material for future worlds. Even as we stand in awe of the power of these explosions, we can take comfort in knowing that they contribute to the ongoing story of creation in the cosmos, connecting us intimately to events that at first seem so distant and destructive. We truly are at a new frontier of awareness. Our instruments have become an extension of our senses, keeping vigil for any sign that the cosmos is stirring with something extraordinary. Scientists from every corner of the globe, using observatories separated by oceans and continents, work together in near real time to witness cosmic events. In those moments, differences of language, culture, and nationality fall away. What remains is a shared human exhilaration at uncovering a piece of the universe's grand puzzle. The sky speaks, and humanity, collectively, listens. Far above, in the stillness of a quiet night, one can look up and feel that even when all seems calm, the universe may at that very moment be experiencing something phenomenal. Thanks to our widened ways of listening, we could become aware of it. Perhaps a detector in Europe feels a tiny ripple in spacetime, and within minutes telescopes in the Americas or Asia capture a new glimmer in the dark. It's both a thrilling and a comforting thought that we are no longer in the dark about these cosmic dramas. We stand vigil, together, attentive to the cosmos. The documentary of the cosmos is still being written and narrated through these signals, and we're fortunate to tune in, to follow along, chapter by chapter. In calm readiness, we await the next cosmic message, confident that we have the tools and knowledge to embrace it. The universe will continue to speak, and we are prepared to listen and learn as the adventure of understanding gamma-ray bursts continues to unfold. In the silent void above Earth's atmosphere, a vigilant spacecraft drifts in darkness. It circles the planet every 90 minutes, gliding over day and night. From that lofty perch, it gazes at the cosmos with unblinking electronic eyes. For this sentinel, day and night have little meaning. Whether it flies above sunlit clouds or over the darkened face of Earth, its gaze remains fixed outward on the star-filled void. This satellite is one of several guardians posted high above, beyond the reach of air. They keep patient watch over the entire sky, waiting for the faintest sign of an immense cosmic explosion. They must live above our protective atmosphere, because down on the ground, we would be blind to the burst's initial cry of gamma rays. Earth's blanket of air mercifully blocks these intense rays. So to catch a gamma ray burst in the act, our observatories had to slip the bonds of Earth and float free in space. Orbiting Earth at different heights and angles, a fleet of such sentinels stands guard. NASA's Swift and Fermi satellites are among them, accompanied by international partners with their own space observatories. Some ride on dedicated missions, others piggyback on satellites with multiple purposes. Together, these detectors weave a network around the planet, each one tuned to catch the briefest flash of gamma energy. Each uses its own method to sense the invisible burst, a scintillating crystal that lights up when struck by gamma rays, perhaps, or a coded mask casting a shadow that reveals the burst's direction. Individually, a satellite can watch huge portions of the sky, but often it is the collective vigilance of all these eyes that ensures a burst from any quarter of the heavens will be noticed. If one sentinel doesn't have the burst in its view, another might. In this way, nearly the entire sky is under surveillance, every hour of every day. It is a silent, unending vigil maintained for the rare moments when the universe decides to call. Gamma-ray bursts do not announce themselves on any schedule. They can erupt at any time and in any part of the sky. On average, a burst that is noticeable to our instruments might happen somewhere in the universe, roughly once each day. Yet this is just a statistical whisper of predictability. In reality, weeks might pass without a peep. Then suddenly, 2 bursts could arrive on the same day. The randomness means those satellite eyes must always be open and recording. There is no warning, no countdown. A burst will not wait for us to be ready. So the detectors simply watch continuously, letting data stream by until the moment something extraordinary appears. Then, without warning, the moment arrives. One of the orbiting sentinels suddenly detects a surge of gamma rays far above the usual cosmic background. In milliseconds, its instruments register a sharp spike of energy. After so many hours of quiet, the satellite's electronic heartbeat quickens. Onboard software recognizes the signature of a gamma ray burst and immediately flags the event. Data buffers fill with the burst's details: timing, intensity, a preliminary patch of sky from which it came. In the darkness of space, the Sentinel has heard a cosmic call echoing across eons. It is the very signal it was built to find. In the instant the burst is detected, the satellite's mission shifts from observation to alert. Onboard computers have already recorded the critical details: the time of the burst and a preliminary position in the sky. Now they assemble a short report of the event. Within seconds of the detection, this report is beamed down to Earth as an encoded radio transmission. A quiet signal travels across tens of thousands of kilometers to reach a ground station, listening for the satellite's call. The burst has spoken, and the satellite becomes its messenger. On the ground, in a quiet control room thousands of miles away, a computer intercepts the satellite's message. Instantly, software passes the data. A new gamma ray burst is identified, with coordinates pinpointing a particular patch of sky. There is no blaring alarm bell, only lines of text on a screen and a swift relay of information onward. In an automated sequence refined over years, a global alert is generated. A data packet zips through the internet, addressed to observatories and astronomers around the world. In less than a minute after the cosmic flash was first caught in space, word of it has already travelled across Earth. For astronomers and observatories tuned into these alerts, the news arrives like a quiet whisper in the night. In a mountaintop observatory control room, a soft ping sounds from a speaker, alerting the technicians on duty. Halfway around the world, a scientist's phone buzzes on a bedside table with an automated text. A new burst, coordinates attached. The message itself is concise, a coded designation for the burst and its location in the sky. To anyone outside the field, it would look like a string of random numbers, but to those waiting for it, it carries electrifying meaning. In essence, it says, a cosmic explosion has just been detected at this spot in the heavens right now. Within seconds, robotic telescopes across continents receive the same notice and pivot on their mounts, beginning to slew toward the target. No human needed to intervene. They were pre-programmed to respond to exactly this kind of call. Meanwhile, astronomers everywhere who see the alert feel a rush of excitement. Whatever they were doing, they now know that at this very moment, a fleeting beacon has ignited in the sky, and time is of the essence. In this way, a burst that erupted untold light years away is swiftly transformed into a call to action on Earth. A silent cascade of signals, first from the satellite to the ground, then through the digital web, has alerted those who listen for such things. In minutes, dozens of eyes, both human and robotic, know exactly where to look. The universe has whispered of an extraordinary event, and the world's telescopes are already turning their attention to that fleeting spot in the sky. All of this unfolds in mere moments, quietly and efficiently, heralding the beginning of an astronomical chase. Under a clear midnight sky, a robotic telescope at a remote observatory springs into action. Moments ago, it received the coordinates of the burst, and now its motors hum quietly as it slews toward that target patch of darkness. In under a minute, the telescope has swiveled into position. Its dome shutter slides open to the night, and a sensitive camera begins capturing an image. Within that very first exposure, a new pinprick of light glows among the familiar stars, a pinpoint that wasn't there just moments before. This is the burst's afterglow, caught in visible light mere moments after the explosion. It already begins to fade, but for now, it still outshines the distant galaxy that is its home. Far above the Earth, another set of eyes is already on the case. The same satellite that sent out the alert can often turn its own instruments toward the burst. For example, Swift carries an X-ray telescope and an ultraviolet optical telescope on board, and within a minute of the trigger, it will have slewed to observe the burst's location. Even as ground-based telescopes are still responding, Swift is already gathering X-ray and UV light from the afterglow. In those first few minutes, Swift's X-ray detector typically spots a rapidly fading source at the burst's position, the X-ray afterglow. Recording this early X-ray emission gives scientists an immediate sense of how bright the burst was and how quickly it is dimming. At the same time, Swift's optical camera may also capture the afterglow if it is bright enough, pinpointing the exact source in the sky. Because Swift observes from space, it isn't limited by Earth's day-night cycle or weather. Even if a burst erupts under cloudy skies or in daylight for ground observers, Swift can still witness it from orbit. In this way, at least one set of eyes is assured to catch those crucial first photons of the afterglow. At a major observatory housing a large research telescope, a human team also springs into action. Imagine an astronomer who, moments before, was quietly collecting data from a distant galaxy when the burst alert arrives. Immediately, they decide to interrupt their planned observations, something that protocols at many observatories allow when such rare cosmic events occur. With quick coordination, the observatory switches to target the new burst. Within a couple of minutes of the alert, the giant telescope's dome is rotating toward the burst's coordinates. The previous work is set aside without hesitation. Capturing the afterglow is now the top priority. Though these moments are tense, they unfold with practiced efficiency. The observatory staff and systems have prepared for this scenario, often running drills for sudden targets. Now they must set up the appropriate instrument to catch the fading light. Perhaps they first use a wide-field camera to locate the afterglow against the star field. Once it's found, they might quickly switch to a more sensitive imager, or even a spectrograph if the afterglow is bright enough to analyze its light in detail. In the control room, each person knows their role. Some are focusing on pointing the telescope and locking onto the target, others on calibrating the instruments and setting exposure times. A lead astronomer may already be coordinating with colleagues at other observatories via instant messages, ensuring that efforts complement each other. Through dim red lights in the control room to keep night vision, you might see calm faces reflecting screens of data. Every minute that passes means the afterglow is fading, but they work swiftly and calmly, aware that this is likely their one chance to record the burst's early behavior. Those first minutes are critical, because the afterglow's brightness often plummets quickly. Just like an ember glowing fiercest right after a fire is stirred, a burst's afterglow is typically brightest immediately after the explosion, and then rapidly fades. In many cases, the light can diminish by half or more in a matter of minutes. That means observations taken at 2 minutes after the burst might see an afterglow far dimmer than at 1 minute. Thus, being even a minute late to observe can mean missing the brightest phase of the event entirely. Moreover, unique physical processes unfold in this early window. For instance, as the blast wave expands, a reverse shock, like a fleeting flash in the fireball, can briefly make the afterglow brighten or flicker. These subtle signals, whether a tiny flare or a sudden color change, last only briefly. To catch them, telescopes truly have to be watching almost immediately. If telescopes are not already watching, such clues about the burst's physics would simply slip away into the darkness along with the fading glow. One remarkable burst demonstrated just how fleeting this early brightness can be. In 2008, an especially powerful burst produced an afterglow that for a short time was visible to the naked eye. For about half a minute, a person under a dark sky could have seen a new star-like point of light where none had been before. But that glory was brief. Minutes later, the afterglow had dimmed below human visibility, sinking back into obscurity to all but telescopes. Only because automated telescopes reacted instantly were astronomers able to capture that flash of brilliance. It was a vivid reminder that if we blink, we might miss even the brightest burst's fleeting peak. After capturing the fading afterglow, the next step for many observatories is to spread its light out into a spectrum, a rainbow of information. By inserting a prism or a diffraction grating into the path of the telescope's beam, astronomers can split the single point of light into its component colors. On the detector, the afterglow that appeared as a single star-like dot now becomes a faint band of color, stretching from blue to red. It is a delicate smear of light, but within that smear lie telltale patterns. Across the rainbow, one can see dark gaps and thin, bright lines. These lines are the fingerprints of elements, atoms and ions that lie between us and the burst, etched into the light of the afterglow as it travelled across space. Astronomers carefully examine those spectral lines and compare them to known atomic signatures. They soon notice something profound. The lines are all shifted from where they would normally be if the light were nearby. Familiar patterns, like those of hydrogen or iron, appear at slightly redder wavelengths than expected. This shift toward the red end of the spectrum is a direct consequence of the universe's expansion, stretching the light waves during their journey. From this redshift, the burst's distance can be calculated. It often turns out to be staggering, billions of light years. Realizing the burst happened so far away, in a galaxy at the other end of the cosmos, also drives home how truly powerful the explosion must have been. To shine that brightly across such an immense gulf means the energy released was extraordinary, momentarily outshining entire galaxies. The scientists at the telescope feel a mix of astonishment and affirmation. Astonishment at the sheer scale of this event, an affirmation that they are indeed witnessing one of the universe's most extreme phenomena. In this way, the spectrum provides a double confirmation. It pinpoints where and when the event took place in the cosmos, and it underscores the tremendous energy that was unleashed. Beyond distance and energy, the spectrum also sheds light on the burst's immediate surroundings. Most of the absorption lines we see come from the gas in the host galaxy where the burst occurred. By examining which elements appear and how strong their lines are, scientists can gauge the environment's composition. For example, if they detect significant traces of heavy elements like iron or magnesium, it means the host galaxy has been enriched by previous generations of stars that lived and died there, seeding the gas with those metals. The spectrum can also reveal whether the burst took place in a dense, dusty region, or a clearer one. If the afterglow's light is missing some of its blue component, or if it shows a telltale dip at short wavelengths, that's a sign that dust in the host galaxy has absorbed the bluer light, reddening the afterglow. Such evidence of dust implies the burst might be embedded in a thick star-forming cloud, perhaps shrouded by the very material that fueled its star's formation. On the other hand, if the spectrum looks especially clean, with only a few thin absorption lines and no significant reddening, it suggests a more pristine environment, with little dust between the burst and us. All these spectral clues together help paint a picture of the burst's home. From this rainbow of information, astronomers discern not only how far away and energetic the explosion was, but also the type of galaxy and conditions in which it occurred. In a few cases, astronomers have even seen the polarization of a GRB afterglow change as time goes on. For instance, the polarization might start at one orientation and then rotate to a different angle as the hours pass, or the degree of polarization might rise and fall as the afterglow evolves. This hints that the geometry of the emitting region, or our viewing angle to the jet, is shifting, perhaps as the jet expands and slows. The once organized magnetic field patches fragment relative to our line of sight, causing the polarization signature to drift. Alternatively, there could be multiple zones in the afterglow, each with its own magnetic alignment, each dominating at different times. By monitoring those changes, scientists watch the jet's compass needle swing, tracing the hidden structure of the blast. Weeks after the burst, long after the visible glow has vanished and the X-rays have faded, a gentle afterglow can still persist in another form. It arrives not as light we can see, but as radio waves, the invisible, long wavelength whisper of the explosion. In many ways, these are like the final embers of a dying fire. The burst's initial blaze is gone, but a faint warmth remains, detectable only with specialized instruments. Astronomers point giant radio dishes or networks of antennas toward the burst's location, hoping to pick up that subtle signal. In the silence of those late days, the radio detectors often find it, a tiny hum of energy coming from the site of the explosion. It is the afterglow's last stand, glowing softly in radio frequencies, while all else has gone dark. Detecting this radio afterglow is a bit like trying to hear a whisper in a noisy room. The signal is incredibly faint, often buried under the constant background hiss of the universe. Radio astronomers use powerful arrays, like the multi-dish, Very Large Array in New Mexico, to listen with utmost sensitivity. Even then, they must carefully process the data, filtering out noise from our own galaxy and earthly sources to reveal the whisper from the burst. When they finally isolate it, a tiny bump in the radio spectrum at precisely the burst's location, it's a quiet triumph. That faint detection confirms that the afterglow is still alive, gently radiating long after the fiery flash has become a memory. Astronomers also chase the afterglow in the millimeter band, frequencies higher than radio but lower than infrared. They often use the ALMA array in Chile, perched high in the desert, to escape atmospheric moisture. Even so, millimeter observations are tricky. Water vapor can easily drown out the faint cosmic signal in static snow. But ALMA's sensitive antennas, working in unison, cut through most noise. If a millimeter afterglow is present, a slight rise in signal will appear at the burst's position. These millimeter data are especially valuable because they bridge the gap between the higher frequency light and the longest wave radio emissions. By filling in this middle part of the spectrum, they show how the afterglow evolves as the blast's shockwave expands and cools. Over the following weeks and months, astronomers continue to monitor the radio and millimeter emission. Often, the radio afterglow will brighten slightly to a peak days or weeks after the burst, then begin a slow decay. They plot the subtle rise and fall of the radio emission, logging each data point meticulously. By charting this ebb and flow, scientists glean valuable clues about the blast's aftermath. For instance, a bright, long-lived radio afterglow hints at a denser environment around the burst, while a weak, short-lived one suggests a more sparse medium. If they observe a sudden change in the fading rate at some point, a steeper drop-off, known as a jet break, it suggests that the once narrow jet of the explosion has spread out and slowed down, transitioning into a more spherical blast wave. In essence, these late-time radio cinders allow astronomers to confirm and refine their understanding of the explosion's true energy and the environment it expanded into. Even after the initial flash has faded into memory, the story continues in these faint murmurs. No chapter of the burst's life goes unobserved. For a long time, scientists wondered if gamma-ray bursts might produce even higher energy light beyond the X-ray energies of their afterglows. Most assumed that once the prompt flash and afterglow passed, nothing significant would emerge at even higher energies. But nature had a surprise in store. In recent years, a few GRB afterglows have been caught shining in the very high-energy gamma-ray band, energies far beyond what our satellites can detect. These photons are so energetic that each one carries billions of times more energy than a visible light photon. The discovery that they were coming from an afterglow left astronomers astonished. It meant that even as the burst's visible and X-ray light was fading, something in the explosion was able to boost some radiation to extraordinarily high energies. Catching these ultra-energetic gamma rays required a different kind of telescope. Instead of satellites, astronomers use ground-based observatories that watch the sky for brief flashes of light caused by high-energy particles. On dark, moonless nights, arrays of large mirrors, like the MAGIC telescopes in the Canary Islands and HESS in Namibia, stare upward, waiting. When a gamma ray of extremely high energy strikes the upper atmosphere, it triggers a cascade of particles that race toward the ground faster than the speed of light in air. These particles emit a faint, bluish glow called Cherenkov light. In a split second, the mirrors catch that glow, and sensitive cameras record it. From those elusive flashes, the direction and energy of the original gamma ray can be deduced. In 2019, one such array detected a burst of Cherenkov light coming from the direction of a recent GRB. It was the first definitive capture of a GRB afterglow in the tera-electron volt range, a true milestone. A wave of excitement rippled through the astronomy community, knowing we were witnessing energies from a burst that had never been seen before. This groundbreaking detection opened a new chapter of exploration, prompting theorists to reconsider how a GRB's shock could accelerate particles to such extremes, and inspiring observers to seek out more bursts that might likewise light up the very high-energy sky. For scientists, the appearance of these ultra-high-energy gamma rays in a GRB afterglow was both thrilling and puzzling. It meant that the blast's outflow was somehow accelerating particles to energies far beyond what had been observed before. One likely scenario is that electrons swirling in the GRB's shockwaves were boosted to near light speed and then collided with lower energy photons, punching those photons up into the tera-electron volt range. This kind of process, known as inverse Compton scattering, requires a combination of intensely energetic electrons and abundant seed photons, a sign of just how extreme the environment around the burst's jet must be. In other words, the GRB's jet was acting like a cosmic particle accelerator, flinging particles to almost unfathomable energies. This realization confirmed some theoretical predictions that had lingered for years, but seeing it in reality was a watershed moment. It told astronomers that GRB afterglows can be even more energetic than we imagined, and that our models of jet physics need to account for these new heights. At the same time, it raised new questions. Why did we only see this high-energy afterglow in certain bursts? What special conditions enabled it? Perhaps only bursts with strong magnetic fields, or especially prolonged energy release, produce these TV glimmers, a possibility scientists are now eager to explore. In the gentle afterglow of a gamma-ray burst, there is a secret hidden in the light, not in its color or brightness, but in the way the light waves are oriented. This property, called polarization, can reveal surprising details about the burst's inner workings. Normally, the light from an astronomical object has waves vibrating in all random directions. But under certain conditions, often due to magnetic fields or specific geometric arrangements, the waves can become partially aligned or polarized. To detect this, astronomers use special polarizing filters on their telescopes. They rotate the filter while observing the afterglow to see if the light gets slightly dimmer or brighter at certain angles. It's a very delicate measurement, since a GRB afterglow usually isn't extremely polarized, perhaps just a few percent at most. Yet even a 1% or 2% polarization is enough to get scientists excited, because it means that amidst the chaos of the explosion, there was some underlying order in how the light was emitted. Perhaps the burst's jet carried a coherent magnetic field across it, threading through the hot plasma as it shot outward. When electrons spiral around such aligned magnetic fields, a process called synchrotron emission, they naturally emit polarized light. If the magnetic field in the emission region was mostly uniform in one direction, the afterglow's light would be measurably polarized. On the other hand, if the field lines were jumbled in every direction, any polarization from one part of the jet would cancel out with another, yielding near zero net polarization. Thus, detecting polarization is like seeing a fingerprint of the burst's magnetic fields. A higher polarization percentage, say 5 or 10%, would shout that the jet's magnetic field was surprisingly ordered, at least for a time. A low polarization, or none at all, would whisper that things were largely chaotic and tangled. Interestingly, polarization in some GRB afterglows has been observed to change over time. For example, the polarization angle, the direction in which the light's electric field vibrates, might start at one orientation and then rotate to a different angle as the hours pass, or the percentage of polarization might rise and fall as the afterglow evolves. This suggests that the geometry of the emitting region, or our perspective on the jet, is shifting as the explosion unfolds. Perhaps as the jet expands and slows, the magnetic field that was once coherently oriented begins to tilt relative to our line of sight, causing the polarization we measure to drift. Alternatively, multiple zones of the afterglow could each have their own magnetic alignment, with different zones dominating the emission at different times. By monitoring those changes, scientists trace the jet's compass needle swinging, mapping out the hidden structure of the blast. Long after the afterglow has faded to darkness, astronomers continue their vigil at the burst's location. Now they are looking not for a fading point of light, but for a faint background glow, the burst's host galaxy. Once the glare of the afterglow is gone, sensitive deep exposures with large telescopes often reveal a tiny smudge of light at that spot. That smudge is the galaxy in which the gamma-ray burst occurred, previously too faint to notice. Finding it is like discovering the hometown of the explosion. With careful measurements, they pinpoint the galaxy's position and confirm that this was indeed the burst's home. the place where a massive star lived and died, or where two stars collided to give rise to the burst. These host galaxies have told us a lot about where gamma-ray bursts come from. Long-duration bursts, those from collapsing massive stars, often reside in humble, faint galaxies that are nonetheless rich in star formation. Many gamma-ray burst hosts are small, irregular galaxies or dwarf galaxies that churn out new stars at a rapid pace. They frequently show low levels of heavy elements, which may enable the formation of extremely massive stars, the kind that end their lives as GRBS. In essence, these bursts love cosmic backwaters that are teeming with youthful stars. On the other hand, the short-duration GRBs, thought to come from neutron star mergers, have been found in different neighborhoods. Some short bursts occur in large, older galaxies, even in galaxies where new star birth has nearly stopped. Others are spotted at the outskirts of their host galaxies, as if their progenitor stars travelled far before finally merging. This contrast paints two distinct origin stories, one in lively stellar nurseries, the other among ancient stars or kicked-out remnants. GRB host galaxies aren't just important for understanding the bursts. They also offer a window into star formation across cosmic history. Gamma-ray bursts are so bright they can be seen from extremely far away, even when their host galaxies cannot. As a result, a GRB can act like a flare, illuminating a distant, otherwise undetectable galaxy. For astronomers, a single GRB can thus unveil a galaxy at the edge of the observable universe. Some of the highest redshift galaxies known were first pinpointed thanks to a gamma-ray burst afterglow, guiding our telescopes to them. In those cases, we're witnessing stars forming in the early universe through the brief light of a burst. By studying those faint host galaxies, astronomers glean insights into what the universe was like when it was only a fraction of its current age, how actively stars were forming, and what those early cosmic neighborhoods were made of. In essence, GRBs help map out star formation in the far reaches and early epochs of the cosmos, serving as beacons that highlight where massive stars lived and died long ago. Even the immediate surroundings of the burst, the cosmic weather in its neighborhood, can be probed by careful observation. As the blast's shockwave expands, it may travel through regions of space with varying density. A massive star that went supernova as a GRB likely blew a strong stellar wind beforehand, carving out a bubble of lower density gas around it. Beyond that bubble's edge, the ambient gas of the galaxy could be much denser. When the afterglow's shock encounters a sudden jump in density, say, when it exits the tenuous bubble and slams into the wall of denser interstellar medium, the interaction can produce noticeable signatures. For example, the afterglow's light curve might briefly brighten or change its fading rate, signaling that the shock hit a denser wall of material. Astronomers have caught hints of such events, a dip or bump in the X-ray or optical afterglow that appears at just the time you'd expect the shock to be ploughing into a new medium. By modelling these light curve features, they infer what the environment immediately around the burst was like, whether it was a relatively clean, hollow cavity or a thick soup of gas and dust. In essence, the fading light can carry an echo of the star's final surroundings, allowing scientists to read the local cosmic weather that the dying star created. When a new GRB is detected, the rush to observe is matched by a rush to communicate. Within hours of the burst, a stream of raw reports flows through the astronomy community. One team reports an optical afterglow at a certain brightness and position. Another sends word of an X-ray spectrum with unusual features. Yet another announces a preliminary redshift, hinting at the burst's distance. At first, This torrent of information is a jumble of puzzle pieces. Some data arrive with uncertainties or even apparent contradictions. Perhaps two observatories measure slightly different brightnesses, or an early redshift estimate gets revised. But as these pieces are shared openly and rapidly, a clearer picture begins to emerge. All this raw information is sifted and compiled in near real time. Astronomers post quick analyses and updates via formal channels like GCN circulars or more informal forums, essentially brainstorming together across continents. In one update, a team might confirm the burst's redshift and thus its distance. In another, someone notes that the afterglow's light curve looks unusual, perhaps a sign of a dense environment or a binary companion. Piece by piece, these contributions turn disjointed data into a cohesive narrative. Within a day or two, a rough consensus usually forms. The burst was at this location in a galaxy at that redshift. It had these peculiar features, or none at all. It likely resulted from a certain type of event. Each astronomer's finding, like a paragraph in a story, joins with others to describe the event as a whole. In the following days and weeks, the picture of the burst grows sharper. Perhaps a week later, a radio telescope's observations confirm the afterglow's late behavior, or a space observatory provides a refined X-ray spectrum. Early hypotheses get revisited. Was that strange bump in the light curve a real feature, or just an artifact of noise? Did the lack of a supernova tell us something important? Scientists begin drafting detailed papers, but even at that stage, they share drafts and insights with one another. By the time results make it into journals, much of the consensus has already been forged through this collaborative process. What emerges is a story of the burst that everyone, in broad strokes, agrees on, a shared understanding born out of many contributions. There is something quietly inspiring about this whole process. In mere days, what began as a fleeting flash of gamma rays becomes a richly documented cosmic event, thanks to dozens of minds and machines working in concert. The raw signal transforms into a shared story that the entire community can tell. And while nearly every detail is scrutinized and understood, there are always a few lingering questions, little mysteries that couldn't yet be solved. Those gaps in knowledge are not failures, but invitations. They point to what might be learned from the next burst and the next. In this way, each GRB not only yields its own story, but also leaves clues for the stories still to come. For all the insight we've gained, there remain aspects of gamma-ray bursts that lie beyond our sight. We have never directly witnessed what happens in the split-second heart of the explosion, the very moment a massive star's core collapses into a black hole, or when two neutron stars crush together into something new. That transformation, the birth of the burst's central engine, is hidden behind layers of extreme physics. Our telescopes catch the furious output, the gamma rays, the rushing jets, but not the engine itself as it forms. We infer and imagine what it must be like, but we cannot yet see it. There are other invisibilities too. If a burst's jet is not aimed our way, the gamma-ray flash might never reach us. We might only catch a whisper of it as a faint afterglow, or perhaps miss it entirely. A whole population of these orphan bursts could be out there, occurring unnoticed because we happen to be looking the wrong way. Even among the bursts we do see, the fine details of the jet structure remain elusive. Is the jet narrow with sharp edges, or does it have a soft, structured profile? We often can't tell for sure, because we only ever see the jet from our particular vantage point. Those internal shapes and variations are largely inferred from the afterglow's behavior, but not directly imaged. We also wonder about the things we cannot touch, even with our best analyses. the essence of the jet itself. What exactly is it made of? Hot matter blasted outwards, or an immense pulse of magnetic energy, or some mix of both? And those magnetic fields that we know are important, are they organized like a giant rotating corkscrew driving the jet, or just tangled threads swept along by the explosion? Our polarization measurements and theoretical models give tantalizing suggestions, but they haven't yet shown us a definitive picture. Until we can somehow probe those inner workings more directly, much about the jet's true nature remains in shadow. Every gamma-ray burst reminds us that discovery is an ongoing journey. With each one, we answer some questions and uncover new ones. We now know so much that these bursts are connected to the deaths of stars and the merging of stellar remnants, that they light up distant corners of the universe and illuminate the history of star formation. But each burst also underscores how much we still don't know. The unknowns are what drive science forward. As long as there are things we cannot see or fully explain, there will be astronomers peering into the darkness, waiting for the next burst, ready to learn from its light. And so the story continues. With each gamma ray burst a fleeting beacon that leaves us with both knowledge and wonder, a reminder of how much remains to be explored. As we continue our journey through the story of gamma ray bursts, our gaze turns further outward and backward in time. These brief, brilliant flashes are not only cosmic explosions, they are also messengers from a distant past. In the silent darkness of space, a burst can appear like a lone lantern flickering at the edge of the cosmic dawn. Its light began its journey billions of years ago, when the universe itself was in its infancy. Now, after an unimaginable voyage across expanding space, it arrives at Earth as a whisper of that ancient time, allowing us to glimpse the universe's first morning light. When a gamma-ray burst reaches our telescopes from across the cosmos, we are witnessing an event from eons ago. There is quiet awe in realizing that the flash we detect tonight might have originated when galaxies were just beginning to form, and the first generations of stars were lighting up the darkness. Imagine the universe less than 1 billion years old, at cosmic dawn, when night was darker and the very first stars were newly born. In that young universe, a massive star lived its life and died in a spectacular blast, unleashing a flood of gamma rays. That flood raced outward in all directions, traversing expanding space for ages. Only now, long after that star and its galaxy have vanished, this burst arrives at our world, a tiny signal carrying ancient secrets from that early era. Each high-energy flash from the early universe serves as a beacon, briefly illuminating its corner of space and time. By detecting these bursts, astronomers learn that even in those early epochs, the cosmos was already active and luminous. One such beacon's faint afterglow revealed an astounding fact. Its light had been traveling for more than 13 billion years. This means the explosion took place when the universe was only a few % of its current age. To put it differently, if the universe were a person about 50 years old, this burst happened when it was just a toddler. In that bygone era, stars were assembling into the first galaxies, and some of the most massive stars were meeting their end in such powerful detonations. The early universe was a very different place, filled with protogalaxies and primordial gas. Gamma-ray bursts from that era show us that the life cycle of stars was already in full swing, surprisingly soon after the Big Bang. Perhaps even the fabled first stars, enormous, hot, and short-lived, could have died in such a flash. though much about those first stars remains mysterious. When we capture the glow of a burst from those times, it is like receiving a postcard from the universe's youth. In the afterglow spectrum, scientists can sometimes discern the faint signatures of elements forged by those early stars. This tells us that by the time of that explosion, some generations of stars had lived and died, seeding their surroundings with heavier elements. The image of a solitary flash shining out from the cosmic dawn is both profound and poetic. For a brief moment, that far-off gamma-ray burst outshines entire galaxies, like a lighthouse sweeping over the cosmic sea. It reveals itself across unimaginable distances, proclaiming that in that tiny corner of the early cosmos, a star met a dramatic end. Then the light fades, and that distant corner returns to darkness, but not before we have caught its message. In the careful analysis of that faint afterglow, astronomers find subtle clues to measure how far the light travelled and how long ago the star died. These measurements confirm that gamma-ray bursts can indeed come from the dawn of time, reaching us from nearly the furthest reaches of the universe. Such discoveries stretch our understanding of the cosmos. It is one thing to study ancient starlight from early galaxies. It is another to witness an actual catastrophic event from those epochs. Gamma-ray bursts serve as time capsules. They carry information about conditions in the early universe that complement what we learn from other sources like distant galaxies or the cosmic microwave background. Each one is like a sudden flashbulb illuminating the scene of a very old cosmic drama. By studying that light carefully, scientists can infer details about the environment of that early explosion. They wonder, for instance, whether the region was rich in heavy elements or still mostly made of primordial hydrogen, and how much dust had accumulated in that young galaxy. The burst's afterglow, spread across different wavelengths, offers answers to such questions, painting a picture of that environment just after the first dawn of stars. We find comfort in the continuity these bursts represent. The fact that gamma-ray bursts from such remote times look broadly similar to those we see from more recent epochs suggests a kind of cosmic consistency. The same laws of physics that cause a massive star to collapse into a black hole or neutron star, producing jets of gamma rays, were at work even when the universe was very young. Seeing that familiar fingerprint of a burst in ancient light assures us that the cosmos, however much it has grown and changed, follows the same fundamental patterns. In a way, it is a gentle reminder that we are connected to those first stars. The deaths of those long-ago suns send light that eventually, patiently, reaches our little world and touches our detectors. From these remote beacons, astronomers also gather hints about how quickly the early universe became hospitable to star formation. If a gamma-ray burst can occur just a few 100 million years after the Big Bang, it means that by then, massive stars had already formed, lived, and died. The cosmic dark ages, that period after the Big Bang before stars ignited, must have ended relatively swiftly. The universe's first morning came sooner than one might have imagined, with stars flickering on like early campfires in a vast night. Each high redshift burst confirms that by those times, enough gas had collected into protogalaxies and formed stars, including ones heavy enough to make such an explosion. Now, as we catch these photons here on Earth, we stand literally in the present and figuratively in the past at once. The experience is almost like time travel by telescope. In the stillness of an observatory night, or the steady watch of a satellite, an alert sounds that a burst has been spotted far across the universe. Quickly, telescopes swivel to capture the fading afterglow, collecting ancient light that has just arrived. It's a race against time. Not the billions of years the light travelled, but the minutes and hours before the afterglow dims below detectability. During those precious moments, the universe is telling us a story from its youth, and we must listen carefully. The scientific payoff from these distant bursts is profound. Their light encodes the expansion history of the universe, a concept we will soon explore, and the state of matter at a time when galaxies were newborn. For instance, by studying one especially far-off burst, researchers identified signatures of basic elements like hydrogen and carbon gas in the space between us and the burst. The patterns of those signatures indicated that the burst's light had passed through material that was already enriched by earlier stars. That means, even by that early epoch, there had been enough stellar generations to produce elements heavier than helium, a sign of cosmic chemical evolution underway. Glimpsing such detail so early in time is something like seeing the faint glow of dawn and recognizing shapes of the landscape in that morning twilight. Gamma-ray bursts at extreme distances let us discern the outline of the cosmic landscape as it was billions of years ago. They help answer when the first stars formed, how quickly galaxies built up their stars and elements, and what the conditions of interstellar space were like long ago. In capturing these signals, astronomers around the world often express a sense of reverence. The data coming through is more than just numbers. It is a direct interaction with a moment in the deep past, conveyed by nature's own extreme beacon. These far-flung explosions underscore how connected different eras of the universe really are. The photons that left a collapsing star when the cosmos was young have travelled all this way and now strike a detector on our planet, which at that time did not even exist. Across time and space, an unbroken line connects that ancient star's demise to our present technology and curiosity. It is humbling and wondrous to reflect on that continuity. The universe, in its vast timeline, offered up these gamma-ray bursts as signals that bridge the eons. As we soak in the idea of lanterns from the first dawn, softly lighting up knowledge of early times, we also begin to notice something about the quality of that light by the time it arrives. These signals do not reach us exactly as they started. They have been stretched and altered by the long journey through an expanding cosmos. The flash that was once intensely energetic and brief has been gentled by the universe's growth. We turn now to the subtle changes imprinted on those ancient beams of light, to how time itself is stretched and softened as the cosmos expands. By the time the ancient light of a gamma-ray burst arrives here, the universe's expansion has left its subtle mark on it. What began as a furious, high-energy flash in a young galaxy is received as a softer and slower glow than it once was. The intervening billions of years have not only dimmed the burst with distance, but also stretched its very spectrum and timing. Just as a stretched spring releases its energy more gently, the flash that raced across an expanding cosmos shows up at Earth in a dilated form. In essence, the universe itself has been expanding during the light's long journey, pulling the fabric of the light waves and spreading out the burst signal in time and space. Imagine a brilliant burst that in its own neighbourhood might have flashed and faded in a matter of seconds. Seen from our far vantage point, that same burst might appear to last noticeably longer. A quick cosmic heartbeat becomes a drawn-out sigh. This effect is known as time dilation, and it is a direct consequence of the expansion of space. The vast gulfs of expanding space between there and here literally stretch the burst's temporal profile. A moment that took, say, 10 seconds in the distant galaxy might arrive here spread over many more seconds. The higher the redshift, Essentially, the greater the stretch, the more pronounced this slowing becomes. It is as if the universe has gently pressed a slow-motion button on the recording of the event. The stretching is not only in time, but also in color, or more precisely, in the wavelength of the light. Gamma rays are the most energetic form of light, yet after crossing billions of light years, even these photons feel the cosmic stretch. By the time they reach us, some of that initially blistering energy has been reduced. Gamma rays might shift down to X-ray energies, and an afterglow that began in the ultraviolet or visible could arrive as infrared. In astronomical terms, the light has been redshifted. Its wavelength stretched toward the red end of the spectrum during the journey. It's analogous to a receding ambulance siren dropping in pitch, though on a far grander scale. Here, it is not the motion of a source through space that causes the change, but the steady expansion of space itself. Astronomers can actually measure this effect in detail. They spread a burst's afterglow into a spectrum, like passing light through a prism, to reveal a rainbow of colors. In that rainbow, they search for familiar dark lines or specific colors that mark elements like hydrogen or iron. These spectral fingerprints normally appear at certain known wavelengths. In a distant burst spectrum, however, those fingerprints show up at longer, redder wavelengths. By measuring how far the lines have shifted from where they would normally be, scientists determine the burst's redshift. That redshift reveals by what factor the universe expanded during the light's journey. It is like reading a cosmic travel log, showing how much space stretched between the light's departure and arrival. The concept might sound abstract, but consider an example. Suppose a certain glow in the afterglow corresponds to a bright line normally emitted by hydrogen atoms at a specific color of ultraviolet light. In the spectrum of a distant burst, that line might no longer be in the ultraviolet at all. It might be observed in the visible red, or even further into the infrared. This means the light has been stretched by that ratio of wavelengths. If it ended up, say, twice as long in wavelength, then the universe expanded to twice its size in the time it took the light to travel. Often, the stretches are much larger. A line emitted in the ultraviolet might be found in the infrared, implying the universe expanded several times over during the transit. In one extraordinary case, a burst's afterglow indicated a tremendously high redshift. At that distance, the universe was less than 1/10 its present size when those photons set out. That burst's light had been traveling for almost the entire history of the universe. As a result, the expansion of space had slowed and gentled its arrival by the time it reached us. It is remarkable that we could still detect it at all, a faint echo from near the cosmic dawn. Time dilation in gamma-ray bursts was noticed even before we had such clear spectra for all of them. In fact, researchers observed that faint, distant bursts often seem to unfold more slowly than nearer, brighter ones. This was a hint that the far-off explosions were being seen in slow motion due to cosmic expansion. It was a quiet clue, hidden in the statistics of burst durations, that helped convince astronomers that gamma-ray bursts were truly cosmological in origin and not just local flashes. The universe itself was acting on these signals, stretching out their light curves in a gentle tug-of-war across billions of light years. This stretching has an intriguing consequence. Every distant gamma-ray burst carries a record of the universe's expansion. The degree to which its signal is slowed and reddened reveals how much space stretched along its journey. Each burst becomes a messenger of cosmic history, reporting not only its own explosive story, but also the growth of the universe while its light was in transit. By collecting data from many bursts at different distances, Scientists can sketch out a timeline of cosmic expansion. Each burst's redshift marks a point on that growth timeline. Together, these measurements, along with those from supernovae and distant galaxies, refine our understanding of how the universe's expansion rate has changed over the ages. It's remarkable how something as violent as a gamma-ray burst can be turned into a delicate tool for cosmology. The key is in the subtle changes, the softening of the light's energy and the lengthening of its duration. These are gentle imprints, almost like the universe's fingerprints on the signal, telling us that the journey was long and the cosmos has changed along the way. The next time we observe a particularly distant burst, and note that it lingers a bit longer than usual, we are witnessing the effect of billions of years of cosmic history acting on that fleeting explosion. The stretching and redshifting of burst signals is not merely a curiosity, it is fundamental to how we interpret what we see. Without accounting for it, we would misjudge distances and energies. But by understanding this effect, astronomers turn what could be a distortion into a source of information. A burst that seems surprisingly long or unusually low in peak energy becomes a clue that we are looking at an event from the far past. In this way, gamma-ray bursts become not only light sources, but also markers of the expansion of the universe. The quiet fingerprint of cosmic expansion on each burst also assures us of something profound. The laws of physics are consistent across time and space. We see the patterns of atomic lines shifted but intact, meaning those atoms behaved the same way billions of years ago as they do today. We see time dilation exactly matching what our models of expanding space predict, confirming that our understanding of cosmic geometry holds true even over enormous distances. This gentle corroboration from GRBS strengthens our confidence in the cosmic story we piece together. Having looked at how the universe's growth stretches and softens the fury of gamma-ray bursts, we can use this knowledge to dive deeper into what these distant flares reveal about the cosmos. Each burst is a point on a grand timeline, but many bursts together form a pattern. Through their occurrences across different epochs, they trace the rise and fall of cosmic events. Notably, since gamma-ray bursts signal the deaths of massive stars, their spread over time reveals when stars were being born in great numbers. By measuring their distances and placing them in time, astronomers turn these bursts into tracers of one of the universe's most important stories, the history of star formation. And so, guided by the stretched light of these explosions, we turn to what they teach us about when and where stars once bloomed. When we map out gamma-ray bursts across the vast timeline of the universe, a story emerges about the life cycle of stars. Each burst, born from the death of a massive star, marks a moment when a star's life came to an end. If we collect all those moments and arrange them in time order, we see patterns that echo the periods when stars were being born in abundance. In effect, the frequency of these distant bursts serves as a cosmic census of star formation. The more bursts we find at a given epoch, the more stars must have been living fast and dying young around that time, fueling these tremendous explosions. Astronomers use gamma-ray bursts as tracers of the cosmic star formation history. By determining the distances, and thus ages, of many bursts, they can tally how many occurred in each era of the past. What they have found aligns with other measures of star birth. There was a golden age of star formation, and the bursts bear witness to it. Billions of years ago, when the universe was only a few billion years old, the rate of star birth reached a peak. Galaxies were fertile nurseries, rapidly turning gas into new stars. In those epochs, massive stars were abundant, and many of them met their demise as gamma-ray bursts. Thus, we see a higher concentration of GRBS from that distant time. Through gamma-ray bursts, afterglows, astronomers can probe the intergalactic medium at different stages of cosmic history. Before we could even see infant galaxies directly, bursts were already hinting at conditions in the young universe. In those early epochs, much of the space between galaxies was filled with hydrogen gas that starlight had not yet fully ionized. A burst shining through this primordial hydrogen leaves a telltale mark, a damping of its light at the wavelengths of hydrogen. By measuring how deep this hydrogen shadow is in the afterglow spectrum, researchers can estimate what fraction of the intergalactic hydrogen was neutral at that time. One notable burst showed that by around 900 million years after the Big Bang, most of the intergalactic hydrogen along its line of sight was already ionized. This implies that the cosmic dawn, when the first stars and galaxies reionized the universe, was well underway by then. Such findings are invaluable. They confirm that the early galaxies had largely cleared away the hydrogen fog of the cosmic dark ages relatively quickly. A gamma-ray burst, in this case, served as a cosmic neon sign, telling us the era by which the universe had become transparent to starlight. Gamma-ray bursts also help us detect heavy elements in the distant universe. The first generations of stars forged elements like carbon, iron, and oxygen, which then mixed into the gas of subsequent galaxies. When a burst's afterglow shows absorption lines of, say, carbon or iron, we learn that previous stars had lived and died in that region, seeding the cosmos with metals. In this way, gamma-ray bursts allow astronomers to study the chemical enrichment of the universe over time. They have, for instance, detected surprisingly high levels of certain elements in galaxies, seen only a couple of billion years after the Big Bang. Evidence that star formation and supernovae had been busily enriching those galaxies early on. Another advantage of GRB afterglows is their extreme brightness. A burst's afterglow can briefly outshine its entire host galaxy, meaning even one flash can act as a powerful beacon, illuminating whatever lies along its path. Astronomers have long used quasars, the bright cores of distant galaxies, to probe intergalactic gas. Gamma-ray bursts offer a complementary approach. Unlike quasars, which are steady beacons in fixed locations, bursts pop up at random spots across the sky and then fade. Each burst is like a momentary flashlight shining through its particular line of sight, offering a one-time illumination of that patch of the universe. In this way, GRBs allow us to sample the cosmic contents in directions and at distances we might otherwise miss, extending our reach into the universe's expanse. Beyond gas, the fog includes cosmic dust, tiny solid particles, like microscopic grains of carbon and silicates that drift in galaxies. Dust is notorious for blocking and reddening light, and gamma-ray bursts are no exception. When a burst's afterglow travels through a dusty region, some of its light, especially at shorter, bluer wavelengths, is absorbed or scattered by dust grains. As a result, the afterglow's color seen from Earth may be redder or dimmer than it would be in a dust-free path. By comparing the afterglow's observed colors and brightness to what we expect, based on the X-ray or unreddened portions of the spectrum, astronomers can infer how much dust was present and even get an idea of the dust grain size and composition. Studying dust with GRB afterglows has led to some intriguing discoveries. In some distant galaxies, the pattern of how afterglow light is dimmed and reddened by dust differs from what we see in the Milky Way. This suggests that dust grains in those galaxies have a different nature than our local variety. GRB observations have also uncovered galaxies that are surprisingly dusty, implying that significant star formation was already underway early in cosmic history. Conversely, a few very distant bursts showed much less dust than expected, indicating their host galaxies remained relatively pristine. Each burst provides a single data point, but together, these data build a picture of how dust content and properties vary across different eras and galactic environments. Not all gamma-ray bursts produce a detectable optical afterglow. A significant number of bursts are what astronomers term dark bursts, meaning that their afterglow is dim or invisible in the optical band, even though an X-ray afterglow is present. In many cases, dust is the culprit. The burst occurred in a dust-rich region that absorbed the optical light before it could escape. These dark bursts are direct evidence of substantial dust in their host galaxies. By considering them, we avoid biasing our view only toward bursts in clear environments. Instead, they remind us that bursts happen in all sorts of locales, including dense, dusty stellar nurseries, where massive stars are born and die. Every absorption line and every dimming of a burst's afterglow by dust adds a piece to the puzzle of the cosmos. Gamma-ray bursts have now been used to study the content of the universe in a way complementary to other methods. They probe the stuff that is otherwise faint, the thin gas stretching between galaxies, the early remnants of the Big Bang's aftermath, the hidden dust in far-off galaxies. With bursts, astronomers have measured the temperature and ionization of gas in the young universe, detected atomic and molecular clouds on the far side of the universe, and even constrained how transparent space is to different colors of light. Each burst is an experiment, one that nature has already set up for us. All we have to do is observe and decode the results. As we learn about the environments that bursts illuminate, we also become more adept at using them as tools. We come to understand which lines in an afterglow's spectrum indicate a calm, intergalactic medium versus one disturbed by nearby galaxies, or how the presence of certain dust signatures might signal a galaxy rich in recent star formation. In essence, gamma-ray bursts are helping astronomers survey both the visible and hidden components of the universe's matter on the largest scales. They shine through the fog, and in doing so, map it out. Having journeyed through the early universe with bursts as lanterns and used them to probe the cosmic fog, we might wonder how far we can push these tools. Can patterns in their flashes themselves be turned into reliable measures of distance, like lighthouses calibrated to gauge the darkness beyond? Gamma-ray bursts do indeed hold promise as cosmic yardsticks, potentially extending our ability to measure distances across the universe. Yet, as with any measuring tool, they come with quirks and uncertainties. In our next chapter, we will explore the idea of using gamma-ray bursts as distance indicators, the promise and the limits of turning patterns into distance measures. The notion of using gamma-ray bursts as cosmic yardsticks is both alluring and challenging. On the surface, GRBS seem like ideal distance markers. They are immensely bright and can be observed across the observable universe, far beyond the reach of other reliable indicators like Type 1 supernovae. If we could decipher a consistent pattern in their behavior that correlates with their true brightness, we could use that pattern to estimate how far away they are. In theory, this would allow us to extend the cosmic distance ladder to epochs and distances previously unattainable. Indeed, astronomers have hunted for such patterns within the complex signals of GRBS, and they have found a few promising clues. One example of a pattern is a relationship between the color energy spectrum of a burst and its total energy output. In essence, more powerful bursts tend to peak at higher frequency gamma rays compared to less powerful bursts. By measuring a burst's peak photon energy, and correlating it with its overall brightness, researchers can attempt to estimate its true luminosity. Another clue comes from timing. Bursts that flicker more rapidly or show a shorter time lag between their high energy and low energy light tend to be more luminous. These correlations hint that GRBs are not completely chaotic. There are underlying regularities that might be used as a kind of calibration. Using such correlations, scientists have constructed preliminary Hubble diagrams, plots of distance versus the redshift of the burst, that include gamma-ray bursts. They appear to fit into the same cosmic expansion story told by more established distance markers. Because GRBs reach far greater distances, they have the potential to probe the universe's expansion at times well before the oldest supernovae can be observed. This could provide insight into questions like how dark energy behaved in the early universe, or whether our cosmological models hold true in those distant realms. However, using gamma-ray bursts as yardsticks must be done with great caution. Unlike the near-uniform behavior of Type 1, a supernovae, gamma-ray bursts are highly diverse. The empirical patterns discovered, whether linking spectral peaks to energy or flicker rates to brightness, show a lot of scatter. There are bursts that don't fit the trend, and we don't fully know why. It might be due to intrinsic differences in the bursts themselves, different progenitor stars or explosion physics, or extrinsic factors like how the burst's jet is angled towards us, or the environment around the burst. Because of this variability, any distance derived from a gamma-ray burst is much less precise than one obtained from a standard supernova. Another major complication is calibration. With supernovae, many nearby examples can be observed and calibrated via independent methods such as parallax or Cepheid variables to set their absolute brightness scale. Those calibrations can then be applied to far-off supernovae. But gamma-ray bursts are so rare and so brilliant that none have been observed in our local universe. We only see them at vast distances. That means we lack an independent yardstick for GRBS's true luminosity. Often, researchers have to assume a cosmological model, informed by supernova data, to calibrate the GRB correlations, then use those same GRBs to probe cosmology. This approach carries a risk of circular reasoning. We are partly using the answer, the assumed universe model, to calibrate the tool that we hope will check the answer. Despite these challenges, astronomers continue working to refine GRBS as distance markers. Each new burst adds data to improve the correlations and to understand their limitations. There is hope that with a large enough sample and deeper insight into burst physics, we might identify a subset of GRBs that are more uniform. Perhaps certain categories of bursts, defined by duration, color, or other traits, will prove to have tighter luminosity relations once we account for all variables. The allure of this effort is clear. Gamma-ray bursts could potentially extend our cosmological reach to redshifts of 8, 9, or beyond, providing a window into the universe's expansion at epochs far earlier than those accessible by supernova. For now, gamma-ray bursts as distance indicators are a work in progress, useful, but to be handled carefully. The term standard candle is seldom applied. Instead, GRBS are sometimes dubbed standardizable candles. This means astronomers must first calibrate them via those correlations, and even then, they are not as predictably behaved as true standard candles. It's a bit like using a flickering torch to measure a room when you're used to a steady laser. It can work, but you have to be cautious and understand your tool's quirks. Nonetheless, the pursuit of GRB cosmology has value beyond the immediate numbers it yields. It pushes us to understand the physics of these extreme explosions better, why those correlations exist at all, and what they tell us about the mechanism powering GRBS. It also extends our reach. giving at least a tentative glimpse into epochs of the universe that we otherwise probe only indirectly. Every improvement in using GRBS as yardsticks tightens the weave of the cosmic distance ladder a little more, adding resilience to our cosmic distance measurements. Even as we marvel at all that gamma-ray bursts can teach us, we are left with a more human question. What if one of these cosmic explosions occurred close to home? Could such a burst pose a threat to life on Earth, or perhaps to life on other worlds under its beam? In the next part of our journey, we will gently explore this question of danger, examining whether GRBS have ever impacted life's history, how our planet's natural shields protect us, and what these powerful events mean for life elsewhere in the cosmos. This adds a personal dimension to the story of GRBS, turning our attention from the distant cosmos back to the safety and fragility of our own world.